Just we are like fully system. Yeah, we are live. We are live.
Sir, we are live on YouTube.
Yeah, it has come, so you can start.
Oh, okay, very good.
It has come. Okay, so there's something wrong with my connection probably. Prashant, hello?
Yeah, it has come, so you start. Yeah.
So maybe my connection is showing some instability. Can you please start? I mean, I'm just worried that...
Not a problem, sorry.
Yeah, I'm here. I'll moderate it. I'm just, the connection is a little unstable. I'm feeling worried.
No problem.
Yeah.
No, I mean, no worries also. It can be self-moderated also.
No, Sai, I am here, I'm telling you, no problem. See, welcome to the afternoon session. So let us welcome Dr. Sai Vinjanampathy from IIT Bombay. Sai is a regular here at IIT Kolkata. He is a regular in all the conferences, workshops on quantum information, quantum technology. Very, very enthusiastic speaker, researcher, and also a very clear teacher. So, you will get to hear from him more because, he works on a variety of areas, starting from, basics of information theory, because if you look at his credentials, you will find out he has passed through all the, great places, and he has in company with really good people. So he not only the basic aspects, but application. And his understanding and explanation of open quantum systems is quite nice. And last time when I heard his talk about this battery and things like that, I was convinced that quantum technology is there. So you will get to hear from him now. You will find judge for yourself. So Sai, the stage is yours.
Okay, thank you very much. So Professor Panigrahi, it's you're too kind as usual. So welcome everyone. So what I want to do today is basically walk you through the basics of variational quantum algorithms. So I say this with basically, let me actually begin with the following, which is that I'm not an expert on this topic. So I mean, this is of course true of everything, but even more so. I mean, I'm even more so not an expert on this topic because this is a topic that is fairly new, and the work on it is evolving very, very quickly. And so the main groups that do it, I have indicated, I work with some of them, but I've indicated basically some names that I often come across. So Elsie Queck, who's my postdoc advisor, his group writes a lot of papers on this. Peter Love from Tufts, Patrick Coles from Los Alamos, Alana Spurguzic's group from Toronto, and Mohan Sarovar from Sandia. And I wanted to flash these names in part, perhaps to advertise their work, but also in part to point out this reference. So if this topic interests you, if you've come here basically to just check it out, then what I want to point out is that there is actually a very nice review that has come out recently, and I'm actually pointing at an archive paper, so it really you can see how recent all of this work is. And so every day you can, when you open QuantPH, you can basically see one more paper. Even today morning I saw a couple of top things on this topic. So what I'm hoping to do as a kind of an interesting experiment for myself, a self-learning method for myself, is I want to introduce this topic to you, share with you what I know about this topic, and hopefully together we can learn a little bit about it. So what I will do is I will present maybe 5 or 6 slides, and then move the conversation to actually a handwritten discussion basically, so that you can actually follow along some of the things that I'm going to talk about. I just wanted to, I thought of it as a kind of summer school style. So I've made it a bit more slower and hands-on. So, so that's why I was telling Professor Panigrahi that I'm happy to kind of, have 1 or 2 more lectures on this topic. Okay, there is one more caveat I just want to present, which is that there is actually, and this field is at the intersection of several fields, as you will soon see. One of them is actually chemistry. Chemistry has a very, very strong interest in this field, and there, of course, I'm not very good with references. So there is Rahul Mitra at IIT Bombay, who I recently discovered. He's just working a couple of doors away from me, and I only recently came to know that he's working on variational quantum algorithms as well. So I give you his name as an example if you're more chemistry oriented, or if you're more your training is more chemistry proximate. but I'm sure that good chemistry folks can point out to you some more names like this, but from the other side, from the chemistry side. This, of course, is written up to be a reviews of modern physics, so this has like hundreds of references, which should be more than adequate as a first and second layer of training. Okay, and before I go on, I just wanted to insert a joke just to lighten the mood. None of this is just the same over Zoom. So I look forward for this pandemic to be over and for me to be back in Kolkata, enjoying the beautiful campus and talking to all of you in person. Okay, so with that, let me start by basically showing you an advertisement of what this field actually is. So what this field actually is all summarized basically in this one very famous paper by Alberto Peruzzo and a bunch of other people. And so the idea is the following. The idea is ground states are actually quite useful. Optimization is quite useful. Ground state optimization is also quite useful. So what I'm showing you here is basically a quantum simulation and the details of how this was done and why this is an interesting field and how we will proceed on this. This is basically the rest of the talk. So if you're surprised or if you're not clear on the details of what I mean by the phrase quantum simulation, just hang on. This is a quantum simulation of basically the dissociation energy curve for the helium hydrogen plus molecule. And so this is what the dissociation curve looks like. And because this is a small enough molecule, there is some quantum chemistry calculation sitting there, which is this red line there. And then there is basically the experimental value, which comes out of a photonic quantum computer. So Jeremy O'Brien is part of this work. And so there is a photonic quantum computer here, which is actually doing the experiment. And then the corrected experiment is the one that's the blue dot. And the blue dots, you can see, track quite clearly the theoretical value underneath. So the bottom line I want you to take away is if I'm interested in asking interesting questions like, hey, what is the bond dissociation for this particular molecule? This is a question that a quantum computer can answer, right? This is statement number one. And the moment you're convinced or you are excited by that question, we already have some sort of a breakthrough in the conversation, because the rest of the story is basically just me trying to convince you how to do this ground state optimization and give you the details of it, right? So let me just add one more sentence here, which is that the reason that chemists are, of course, interested in this, you can immediately see, is basically because this is very useful for discussing any number of properties of molecules, and hence it's useful for drug design. So from chemistry to industry, you can see how basically this is very, very useful as a near-term quantum computing solution, right? And what I hope to give you a little bit of a flavor of today is that how NISC actually participates in all of this. Okay, so with that, let me just say again, I wanted to prepare this. I wasn't really sure who the audience was going to be. I'm sorry, I'm just in the middle of some stuff, so I forgot to ask Professor Panigrahi this question, which is, so here is some basics that the experts will just excuse me for bringing up again. So what types of optimization are we interested in, right? So what I wanted to do was I wanted to start from this point, optimization, which if you're physics students, we know what optimization looks like. We've seen some version of optimization. If you're an engineering student, you've seen optimization, right? If you've done high school calculus, you've seen optimization. What kind of optimizations do we consider? We typically consider optimization of well-behaved functions, right? If we're physicists especially. What we don't consider, which is also valid optimization, is optimization over sets, right? I can say, find me the reddest ball out of a set of balls. And this is not there is no clear property there, but it's a collection of objects. And so what we do when we have functions, on the other hand, well-behaved functions with derivatives and so on, is basically use some sort of gradient methods and use hill climbing and so on and so forth to kind of get on with the program. So higher dimensional functions basically get trapped in local minima and maxima. This is something that I want to just highlight in case you have not come across this point. And this will be useful basically for some specific comments that I will make later on. But this is not going against the general program that I'm trying to talk about here. And but the general program can be summarized in the following way, which is that variational principles can actually be set up as a great tool for setting up a gradient algorithm, right? So this is the point that I just want to emphasize. So here, let us simply, it's always good to start with something that is old and then move to something that is new. So let us start with something that is old, at least to the physics folks in the audience, we know this quite well, which is the calculus of variation. So we do variational principles, actually we do it, but we do very, very specific versions of variational principles. So here is an example of a variational principle. So we might want to actually, so what do we do? So I'm just recollecting the program in general so that you understand the program. So what do? We take basically some quantity, which is called the action. How it is motivated, so on and so forth, is the task of a good first year classical mechanics course. And the action is typically written as the integral over basically some Lagrangian, maybe with time there, but I've just simplified my life for the moment. And then basically what you do is you demand the first order variation of action. So this is essentially the only thing I want you to take away is that the first order variation of action leads to basically a bunch of terms, some of which you can integrate by parts away, and then you end up with the Euler-Lagrange equation. Basically, del L by del QK dot is my d by dt of del L by del QK dot is d by del L by del QK. So you end up with the Euler-Lagrange kind of formalism, basically, by basically starting with a Lagrangian and then just doing first order variation, and I have to formalize. I haven't finished this proof. I have to formalize this proof, and then I'll get the Euler-Lagrange equations. Right? So what I want you to take away is I can start with something like an action, and if I integrate over, if I vary the action over the entire path, then I get a differential equation. On the other hand, I don't have to vary the action over the entire path. I can choose static variation, and I get different answers from it. And so this other kind of variation is perhaps something that is just thrown at us. So I just want to say it out loud with one example, which is unrelated to physics, and then I'll come back to physics. So here is another version of variation, right? And the other version of variation is what you call them, what we all know in high school calculus is basically the Newton-Raphson method. So what is the Newton-Raphson method? I have some function, it's doing something, whatever it's doing. And I just want you to find the local point x star such that f of x star is 0, right? So I want you to find x star such that f of x star is 0. And so what do? I can in general set up a variational principle for it. And this is basically the point I want to drive to those who have not seen variational principles or have seen variational principles in a very limited context. Because once I set up the variational principle, the Ritz variational principle, and kind of and push out one formula, I'm never going to look back at variational principles. So I thought that as an introductory lecture, maybe we should just stare at this for just 30 seconds. So so what I do is I basically set up a variational x. So this variational x simply means I have my target x, I have my trial x. It's some trial function that I choose. So I've indicated several points on this diagram as basically trial points that I can choose. So I can ask, is the functional value of, is the functional value at this point x, is it 0? No, of course not, it's some positive value. Is some functional value 0 here? No, of course not, it's some positive value. Is it 0 here? No, it's some negative value. It's some negative value, so on and so forth. So I could choose any point on this. So if I choose such a point xt, sorry, this should also be xt, then basically what I want is I want my variational, so my next guess in the x, to be a closer value to f of x star, to be a closer value to x star. So I want to travel, so if I start here, I want to travel basically closer and closer to x star. Maybe I just travel like this and like this, or maybe I go from here to here, and then I dance back to positive, dance back to negative, and then finally converge over here, right? I don't know how this is done, and this is all related to basically some properties of the function, so on and so forth. But let's just keep it aside for the moment. And let's just say that I want to introduce, so what do I have? I have some demand, which is I want to find x, right? And minimize the value of x. And what is the value of x what property do I want to hold at that value of x? I want f of x to be 0, basically. And so what I do is these two statements, basically the thing that I'm trying to optimize and the equality constraint, basically, can be accommodated inside a variational principle. This is what we learn in classical mechanics, in a standard classical mechanics course. So what is perhaps emphasized in a classical mechanics course is how to derive the equivalent, basically, constrained Euler-Lagrange equations, to derive the derivatives, to derive the local differential equations. What I'm doing here, on the other hand, is deriving basically a static principle, essentially something that just spits out better and better versions of xt. And this is the version that we will take forward. So, okay. So how do you set up the variational principle? Again, I'm just doing this. There is no reason to do this in what I'm going to show you maybe 6 slides down. But I'm just doing it for pedagogical reasons, just so that you understand where all of this is coming from, where this variational quantum algorithms, where the word variational is coming from. So what I do is I basically vary. I do the first order variation delta x, and I set it to 0. So there are 3 terms here. So there is the variation in xt, which means I could have, instead of this point, I could have chosen a different point. There is the variation of basically this quantity lambda f of x, which I've introduced and I forgot to mention, so let me go back and fix that problem. So whenever you have an equality constraint f of x equals 0, you can always incorporate it into the variation principle with an unknown object which you multiply it with. So this is what we study basically as the Lagrange multiplier. So it's the Lagrange undetermined multiplier. So you introduce a Lagrange multiplier and you multiply it with the function f of x, and you introduce it into the variation principle like this. And how the Lagrange multiplier becomes useful, I'll show you in exactly 2 lines now. So what I do is I now perform the first order variation. So the variational x is basically just the variation in the trial, the variation in lambda, right? But when lambda varies, this quantity is the correct answer. So this is x star, f of x star. But f of x star is 0, so the variation in lambda disappears. This is fairly characteristic of all Lagrange multiplier ansatz like this. And then I keep the lambda, but I vary the x inside the function. So I do delta f by delta x star, delta x trial times delta x trial. But this delta x trial and this delta x trial are the same. So what I do is when I set delta x variational to 0, what I'm saying is that the first order variation is 0, right? It's the same thing that I did here. Delta x, if I set to 0, then I get the Euler-Lagrange equations. I have to finish this proof here. So I set delta x v to 0, but this term in the middle drops out, and there are these 2 terms which are multiplied by a general variation delta xt. And because I have not told you what the general variation, it's a completely generic variation delta xt. You have to take it out common, and what you get is 1 plus lambda f prime, right? So 1 plus lambda f prime is 0, which means lambda is minus 1 over f prime, right? And now if I take this, which determines the Lagrange multiplier is just minus 1 over the derivative of the function, and I plug it back here. My variational ansatz for finding the zeros of a function is that you take the trial function and you subtract from it the function divided by the gradient. And of course, we know this as the Newton-Raphson method, which we derive from basic calculus, right? Is this clear to everyone? So the basic point I want to make is basically that variational principles are actually a minimization program. This is the only reason that this example is sitting on the slide here. And so when I show you that I'm trying to optimize quantum variation circuits and so on and so forth, all of that is basically driven by this exact same philosophy, right? Is this clear to everyone? Okay. So now what I do is, once again, I want to apply this to quantum mechanics. So let me go back to quantum mechanics. And I wish to minimize basically psi h psi. I want to minimize the Hamiltonian expectation value in a quantum state, which of course is minimized by the ground state. So this program, this question I'm asking is the same question as basically demanding that I want the Hamiltonian ground state. So what, again, you can do, I just set up the Euler, the variation principle, but I have not solved it. If you want the details, you can look here. There's a little bit of 1 or 2 lines of trickery involved. So what you can do is you can set up a variational ground state energy, which is the trial ground state energy, plus basically 2 Lagrange multipliers. One Lagrange multiplier enforces normalization of the wave function, and the other Lagrange multiplier simply says, I want h psi to be equal to e psi. I want to solve Schrodinger equation, right? So I want to solve Schrodinger equation. I want the wave functions to be normalized, time-independent Schrodinger equation. I want the wave functions to be normalized. Whilst both of these things are happening, I want the energy to be as small as possible. This is the minimization program that you can restate it in this way. So what you do is this particular normalization ansatz you enforce with an unknown Lagrange scalar multiplier lambda, but the vector h minus e times psi should be the 0 vector. You enforce with a vector Lagrange multiplier, capital lambda that I've called here. So if you do both of these variations, if you do the variation of the whole thing and set it to 0, blah, 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 you will end up with what's called the Ritz variational program. So you will end up with the variational eigenvalue, the variational ground state is basically equal to the trial wave function times 1 minus the normalization, which means that if your wave function is not normalized, you pay a cost and your energy is higher. So for any wave function which produces the same energy, by simply normalizing the wave function, I get a smaller energy. So this enforces normalization. And so typically you can always use an ansatz where the wave function is already normalized. So if you use normalized wave functions, this term drops out. And then basically the variational energy of the ground state is simply just the expectation value in the wave function. So this basically of the Hamiltonian in the trial wave function. This is basically the Ritz variational program, right? Which all of you perhaps will study in a quantum mechanics course, in quantum mechanics 2. Okay, so this basically is an application of the exact same variational program that I just showed you. Previously, I had just shown it to you for a scalar function, but now and the scalar function optimization involves pulling one equality constraint, which is f of x equals 0, enforcing it with a Lagrange multiplier, the scalar Lagrange multiplier, and the the iteration algorithm that we got basically is the iteration algorithm that basically produces the Newton-Raphson method. So already here there are several very, very important theoretical toolboxes for kind of the undergrad education that are available. One is basically we discuss how to deal with equality constraints versus inequality constraints, right? So this can be a point of discussion here. The second is basically Lagrange variables, how they appear inside variational theory. This is also something that appears alongside the discussion. And the third, which is actually equally important for kind of the algorithmic purpose that we're driving towards, is that the variation principle, what it sets up is an algorithm. So you iterate this algorithm over and over again, and you get better and better answers till you maybe just bounce around the minima or just settle on the minima. Right, so this 3 points I want to emphasize, but the third one, that this is an algorithm that you iterate over and over again. This is something that will become important in a second. Okay, then what we did was we applied all of this basically to minimizing the ground state wave function. And here we introduced a Lagrange multiplier, which is a scalar, and another Lagrange multiplier, which is a vector. Right, and just like this, you can also introduce Lagrange multipliers, which are operators and so on and so forth. So this is a kind of rich area for discussion, basically. Okay, so the point I want to move away from this variation principles very quickly so that I get into the algorithms, which is the important bit here. So this was just kind of general purpose education up until now. So the point I want to make is that variation of, let's say, ground states of Hamiltonians over trial wave functions which belong in basically the many body states, the full many body states is hard. Right? And this is hard because entanglement grows very, very quickly. And what that means is that you cannot control for basically the fact that this wave function, if it's in the full space, basically, then you will need a kind of very detailed description of the quantum state. Many, many parameters will be needed. So what can you do about this program? If I gave this program to you, what do you do if you were sitting in a classroom? So the first and the thing that we learn how to do in our quantum mechanics 2 course, our approximate theory course on quantum mechanics, is basically we understand how to apply this with the ansatz that psi of t is optimized over a set S. This S is basically, let's say, a restricted entanglement set. So for instance, I can choose the Fock basis, some sort of product basis ansatz, some restricted, pairwise symmetrized, pairwise anti-symmetrized ansatz. These kinds of things we've learned how to do over our class. Another kind of modern technique that has emerged is basically you can use intermediate levels of entanglement, or maybe you can control the way that the entanglement is growing, and you can use something like DMRG techniques here. And so by basically looking at bond length and bond dimensionality, you can control basically the amount of entanglement. But the thing that I want to emphasize is that both of these solutions that are on the screen right now, you can do either on a pen and paper or on basically a computer, on a classical computer. The third and the most different point of view on this is the one that brings us to the discussion for the next half an hour or so, which is basically that you could use a restricted quantum ansatz. What do I mean by this? This is basically where these wave functions are no longer things that you can specify classically. They have to be specified on a quantum computer. So they're special states that can be produced on a quantum computer. So a quantum computer here is simulating itself. This is the kind of computational power that you're taking advantage of. But it's not the full set of all possible quantum states, because that again becomes kind of complicated and so on and so forth. And so here basically, this basically opens up a whole new avenue of research. And this is the research avenue that I want to introduce you to, which is basically the area of variational quantum algorithms, right? Okay, are there any quick questions up until now, or shall I move on to the next phase?
Sir, can you please explain the last point?
Yeah, so the last point is basically the rest of the talk. So what I'm going to point out to you is that here what I'm doing is I'm writing by hand. I can just write, let's say, product of quantum states, and then I try and find the ground state, right? So there are many techniques that you can use, like this, Gutzweiler ansatz and so on and so forth, where you can just find the ground state by just pen and paper calculations. The next is basically you write a representation down on pen and paper, but you have to implement it on a computer. So you can't, the calculations you cannot do very easily on a sheet of paper, but these are still accessible on a computer. Because what you're doing here is basically, you're doing a kind of Schmidt decomposition, and then you're controlling the number of Schmidt coefficients, and that allows you to basically hold on to a certain amount of growing entanglement in the system. This is basically, I just have a soup of atoms, basically, let's say a chain of atoms trapped in an optical lattice or something like that. And these soup of atoms, I have some restricted control over them. And I use this restricted control to produce a subset of all possible quantum states in that Hilbert space dimensionality. And then I do all my optimization in that space. And if you just bear with me, I will show you that, what is the degree of freedom. So you can say here, basically, I might have some coefficients that I can vary. Here, there are some Schmidt, there is some kind of Schmidt coefficients and stuff like that I can vary. What do I vary over here? In this restricted quantum ansatz, what is it that I vary? Just bear with me. There are parameters of circuits and so on and so forth, which I will show you in cartoons, and then we can start working them out in a more serious fashion. Okay?
So Sai, is there any way to guess? So is this the third recipe is in general more powerful, or it depends on the character of the problem? That what kind of, so is there a general advantage which you have over the first two, or it is indeed some certain types of problem for which this is very powerful?
Yeah, in as much as full quantum states, quantum states with all quantum states in Hilbert space are basically a superset of quantum states with kind of some restricted ansatz of entanglement. This is basically always more powerful. So this will at least give you the same answer that the classical one gives you, or go lower, right? So the question becomes a question of implementability and so on and so forth.
Maybe I rephrase the question. I mean, there is this issue of long range and short range entangled system, right?
Sure.
So the DMRG in one dimension, I think, does deal with reasonably well with short range entangled system. But if it is really long range, do you think that is when you need the third guy, which will do much better than?
Yeah.
Is that the point?
All of these situations, yes, exactly. The point is where you are also out of DMRG. You're also out of the space that DMRG knows how to deal with.
Right. So are those the long-range entangled systems? So this is
for instance, long-range entangled, but also basically you can have computationally. So long-range, short-range is one point of discussion. There is another thing, which is if you have, let's say, 40 qubits, right? Or 50 qubits, however, 100 qubits, right? There is a point where basically, even if you could, in principle, do DMRG on it, in practice, you might run into kind of real trouble.
I see. Even then, you will have an advantage.
But 100 qubits is something that's well within our reach now to do, basically. And so there also, just by sheer numbers, I can break up. So the entanglement is growing however it's growing, but the full computational space might or might not be available to you in DMRG, just from kind of number counting arguments, basically.
I see. Okay. Thank you.
Yeah, sure. Okay. So this is basically the setup at which point I want to introduce to you the solution. And so the solution is basically the following. The solution is the fact that in the news, if you've seen anything in the news, you've seen these kinds of things appear. So this is Google's basically quantum processor, the Sycamore, right? It has like 50, 60 qubits inside it, with some of which are on and some of which are off. And basically, there's no error correction, there's no nothing on top of it. But this is already an engineering feat, which we should all celebrate and we're all excited by in the community. So here, what is the point I want to make? The point is that these are small number of qubits, small in a thermodynamic sense, or in the sense of quantum computing, if you want. They're also noisy qubits. They're qubits with a lot of noise on top of them. So, you cannot really do many body, precise transformations and so on and so forth. There is no error correction, which is another way of saying noisy, because if there was error correction, then noise would be eliminated. And now the question that people were asking already, so I should have cited Preskill's paper here. The question that Preskill was asking already was, what can you do with it? If you can set up algorithms for basically these kinds of, 100 qubit processor, here is some interesting stuff that I can do with it. That is already something that everyone is excited by. And now this is where I tie you back to the question of the molecular ground state or the molecular dissociation energy. If you have the problem be small enough, then indeed you can hopefully basically do something where 100 or a couple of 100 qubits, you should be able to do some simulation which you otherwise classically cannot do, and that doesn't have to wait for a full-on error-corrected quantum computer as well, right? So that space that is sitting in the middle, which is also illustrated by this diagram. So this diagram basically is just trying to show you the number of qubits versus the timeline of their development. So you can see from 1 to basically maybe hundreds of qubits, we're sitting at 2021 here, so we're somewhere here. But the point is basically that we need, if you are trying to implement the two things that we teach undergraduate students in the quantum computing course, which is Grover's algorithm and Shor's factoring algorithm, that starts at 10 to the 4 qubits and above, right? So that starts over here. So there is this whole kind of region, this gap area, where basically engineers, scientists, colleagues of ours, we will have to keep developing these quantum computers. Industrial partners have to develop quantum computers. And it would be nice, basically, if you can fill that space up with explorations of our fundamental understanding of the universe, but also of basically problems that are of interest both to academics and to industry. So this is where basically quantum simulations, quantum chemistry, this quantum approximate optimization algorithms, all of these basically show up in this area. And so this quantum variational algorithms are basically just sitting in this area, basically just a catch-all phrase for all of this stuff. And this is basically the point of my discussion. Okay. So here is basically what running an algorithm on a NISQ device would look like. This basically brings up, so I wanted to show you the big picture first before I kind of broke it down. So there are lots of bits here which you might say, I don't understand, but please hang on and I'll explain all of them. So the first is basically that I want to run something on a quantum computer. So I know vaguely what the cartoon is. The cartoon is that I have some bunch of qubits and then I send them in. There is some unitary gates that act on it, and then there are some measurements, right? This much is very clear to me, right? Now, what I want to do is I'm going to basically take the expectation value of the Hamiltonian that I'm interested in. This is the problem that I mentioned to you, the expectation value of the Hamiltonian as the optimization problem. What I'm going to do is I'm going to break it into 2 bits. One is I'm going to break it into a bunch of parameters, theta and phi. So what these phis and thetas are, we will see as we go along. It's not very important what this particular breakup is. But roughly speaking, there are some parameters that are hidden away into the state preparation part and maybe into the unitary part. And so these parameters are called thetas and these parameters are called phis. And then what I do is I basically take my quantum state, and I prepare basically these phis and thetas, and I send them in and I measure the answer and the answer is also basically depends on the basis change. So think of basis change plus measurement that I'm indicating with my cursor here. Think of basis change plus measurement as being the answer that you're trying to see. Now what I do is based on the answer gives one click, it gives me one number. Based on that, I optimize over the parameters of the quantum circuit, and then I run the algorithm over and over and over again. So you see the difficult bit, which is the wave function of a many-body quantum system, is simply embedded somewhere here. I never have to calculate any of it. The expectation value, which is the ground state expectation value, is embedded somewhere in the measurement, and I don't have to calculate any of it. I'm simply extracting these numbers. So I delegate all of the difficult bit of the physics, which is basically how do you actually compute expectation values of many-body quantum states and optimize over a set of many-body quantum states that can be computationally complex. You delegate all of that away to a quantum computer. And you hold on to basically a parameterization, which you can then simply turn the dials, basically turn the knobs So you have a gradient search algorithm here, classical optimization algorithm here. So this classical optimization can be something like a Newton-Raphson technique. It may be something that you have produced out of a variational principle, so that every time you run this algorithm, it just automatically runs a better and better version. So this updates the values of theta and phi, and it tells you what the new theta and phi are. You just simply plug them in, run them again, plug them in, run them again, till convergence. And this you can basically, by taking the Hamiltonian parameters, so in the dissociation energy, it was the distance on one axis. So by taking the Hamiltonian parameters and putting them into this circuit somewhere, and where is the question? Somewhere, you can basically vary the distance on this axis. And by repeatedly running this optimization on top of that, basically, you can reproduce this kind of a curve, but on a general quantum computer, right? So this is basically running simulations on a NISC device, and this basically ties the two little pieces of the conversation that I hopefully try to explain to you. Okay, so I just want you to note that there is basically this quantum classical loop here. There is a loop which involves basically going through some parts which are purely quantum mechanical, and then after measurement, there is some parts which are purely classical. This is just a standard computer optimization. And then there's some parts which are purely quantum mechanical again. And so this quantum classical are what are also sometimes in the literature, if you look, they're called hybrid algorithms, right? So you'll see hybrid optimization, hybrid algorithms. This hybrid in this case refers to the quantum classical hybridization, basically. Okay, so with that, let me just say to you that there are 4 questions that arise, and what I hope to do today for a little bit, and also over the next lectures, with the organizer's permission, what I hope to do is actually answer some bits of all 4 of these questions. So the first question that you can ask, in no particular order, I've just put them down as they came to my mind, is how do I extract basically this expectation value of psi of some operator A in some quantum state psi, which is parameterized by some theta, right? So now I'm generalizing from Hamiltonian to asking any question, basically. And in fact, if I put a phi here, then I've generalized it completely, but let's leave it alone for the moment and just say calculating expectation values is what I'm interested in. The second question I should ask and answer is basically or the Hamiltonian that I've stuck in. Hamiltonians are not quantum states. Quantum states can be put on a quantum computer. Hamiltonians cannot be put on a quantum computer. What does this question even mean? So how do I represent operators on a quantum computer? This is the next question to ask and answer, because if I don't know the answer to this, then I can't even represent this on a quantum computer. The third and perhaps the easiest is basically, also the thorniest, is how do I represent psi of theta? What really is the way for me to represent psi of theta? Is it basically just you put down whatever and you write whatever, or is there more nuance to this? And the answer, of course, is that there is a bit of nuance here. And I've added a 4th artificial sounding question, which is how do I optimize psi H psi? You could say, well, didn't we resolve this already? You just run a gradient search algorithm or something. When you try and compute gradient, some issues arise. And I want to also point out this as a kind of, invitation for you to go look at the literature and look at the field. Okay, so all 4 of these have answers. So let me just very quickly point out that today what I will do is for the rest of the 20 minutes or so that I have, I'll point out how to do Hadamard testing. And so Hadamard testing will basically answer the first question. The second question is basically answered by what is called linear combination of unitaries, polywords, and block encoding. So I will do linear combination of unitaries and Hadamard testing together, basically. And hopefully this will answer these 2 questions. And the third is basically what is called hardware efficient ansatses or system aware ansatses. So there's a whole literature around this stuff. And this also pulls us into chemistry direction, couple cluster ansatses, and stuff of that sort. How do you encode fermions onto qubits? All of the kind of hard condensed matter questions, basically, and quantum chemistry questions sit inside this a little bit. So this is not a trivial question. I just want to invite you to think about it a little bit more. And the fourth is basically how do I optimize this quantity? Here, basically, there is a very, very famous problem that has come up in the last 2-3 years called the barren plateau problem. And so what I just want to do is basically for the next 20 minutes or so, basically, I just want us to consider one of these at a time, right? So what I will do is I will just stop sharing now. I'll wait for some questions and then I'll stop sharing and I'll move to my iPad where I can write this, and then both the slides and the iPad notes, I'm just happy to share with you through the organizers, yeah? So are there any questions?
Sai, there is one question on this box, which seems to be, what is DMRG? That's the question. Navneet has asked this.
Okay, so yeah, it's not very important for the rest of the discussion of this. Sorry, I didn't mean to unshare. It's not particularly important for the rest of the discussion of this thing. DMRG is a technique where basically it's called density matrix normalization group. So it's a technique where basically you can, in a controlled fashion, grow a many-body quantum state in an ansatz by basically trying to control the amount of entanglement that's in it. So this is I mean, I will say nothing more than this, Sharon, even though maybe I'm doing it underservice, because
No, it's absolutely fine. It's up to you.
Yeah. I have to make sure that the person who's asking actually gets the answer and it's not just an open test for me, because I have to then talk to them about whether or not they understand entanglement.
Yes, absolutely, agreed. And I have a small question, Sai. So does the character of the spectrum decides what algorithm you use, in the sense that if there's a gapped Hamiltonian, in a sense, if the ground state manifold is really separated from rest of the excited states and you are really trying to optimize and get to the ground state, does it make a difference to your algorithm if it is gapped or it is gapless?
Yeah, I think this will make a huge difference, but let me say that gapped versus gapless, the context in which we know this is dynamics, right? So we know this much more in the context of adiabatic quantum computing. To be perfectly honest, I have not kept up, or I don't know the literature on the nature of the gaps affecting the optimization. But I imagine that it will definitely play a role, because so the point is basically, if I start anywhere, so let me just say what I think. If you have a static Hamiltonian, so let's say you have a gapless Hamiltonian or a gapped Hamiltonian, what happens is that if you have a gapped Hamiltonian, then basically any ansatz that you provide, once you hit the first excited state, it really has to jump to the ground state. There is nothing in between. Right? Whereas if you have a gapless Hamiltonian, then you can run through an infinite number of ansatzes that are basically in the middle. So I would imagine that this would play a role, but I really, if there are papers on this, I'm just ignorant, and this is just part of the fact that I've been chewing away on one little corner of this literature. So let me openly confess that I don't.
Thank you, Sai. I just wanted to, thank you.
Okay. Any other questions, or can I switch?
No, you can. I think you can switch, because I don't see any serious question anymore. Yeah, we can move and maybe take on at the end. Yeah.
Okay. So let me just screen share again, but go iPad. Share. Okay. So can you see my screen? So Sharon, can you see my screen?
Yes, very much.
Okay, perfect. Okay, so let me just push some of the stuff around. Okay, perfect. So let me just again recollect what I just said. So there are 4 questions. One is how to extract read basically psi theta a psi theta. 2 is how to represent a. 3 is basically how to represent psi theta, and 4 is how to optimize basically this a theta quantity, right? Quantity. And so what I want to end our discussion for today is basically, I just want to answer these 2 questions and and just make a couple of comments on them, because this is something that that I think is a good introductory kind of little bit to chew on. Okay, so so let me just say, so what do I representing A? So let me take on this this question of representing A. So typically the way A is represented, so remember A is a Hermitian operator, right? If it is not, it's not a huge problem. So let me just say, if I write A as basically H plus I times I, H1 plus I H2, then this is the Hermitian part and this is the anti-Hermitian part, and everything I say, you can break it into this Hermitian, anti-Hermitian, and you can just repeat the conversation. Let me not do it right now, but I just say that this is the fact that this is Hermitian has very little significance in the entire story. Has very little real impact to the rest of what we're saying. Okay, so because A is Hermitian, what I can do is basically, I can say that perhaps I could think of A as the sum over AK times UK. And so this is what is called the linear combination of unitaries, right? And the reason why this is basically called that is basically these UK dagger UK are unitary operators, right? Unitary operators, and basically they're Hermitian unitaries, Hermitian unitary operators, and basically what I then have is well, if they're not, then you need the dagger as well in here. Which is not a problem, but if I, the simplest case which I'm going to discuss right now, they are in fact Hermitian unitaries, and these UKs then consequently are basically real numbers, basically. And so why is this an interesting ansatz? The reason why this is an interesting ansatz is it will be very clear to you the moment I write down any kind of spin Hamiltonian that is of interest to all of us, right? So suppose I write basically omega k sigma k over 2 summed over k plus basically some sum over jij, basically sigma xi, sigma xj, right? Anything that I write like this, just notice the fact that these are all Hermitian unitaries. Right, and these are all Hermitian unitaries as well, and these are all real numbers. Right, and what that basically means that Hamiltonians automatically actually come as linear combination. Many spin Hamiltonians automatically come as a linear combination of unitaries, and these things that are sitting here, which so xi, xj, maybe for kind of fundamental spin physics, this is all you can imagine. But if you start with fermionic operators, ff dagger, then I say this. I make this claim without any further justification, but maybe we can do this on the third lecture or something like that. Then basically, when you do the fermion to qubit mapping, then you just have to trust me that you will end up with objects of the form xi, xj, zk, blah, blah, blah. So you can end up with kind of fairly complicated polystrings. And they have to do with the fact that Pauli's exclusion principle to enforce it at a given site is a non-local affair. So you have to bring basically polystrings from many, many places. So anyway, if this point is not, if you don't understand this point, just ignore it for the moment, and I will re-explain it when I get to this relevant point. The important thing that I want you to take away is XIX, XJ, ZK, and XI, XJ, ZK, stuff of this sort are all examples of poly words, right? So they are basically tensor product of different poly operators which are which appear as strings, right? So they're called poly words, and these poly words basically are implementable on a quantum computer. How do I implement if I just give you this arbitrary operator? It's just basically you put an X on the, I have qubits running this way. On the ith side, you just check and you put an X there. On the jth side, you put an X there, and on the kth side, you put a Z, right? And that kind of a construction of a quantum circuit with no other details that I know already implements XXZ. Right? So it implements these kinds of poly words very easily. So this kind of a poly word can be implemented as well. So you just need to take all nearest neighbors or all possible neighbors, depending on what the Hamiltonian is, and simply implement a product of X's, basically. Right? So
Sai,
yeah.
Can I just interrupt for a clarification?
Yeah.
So are you saying that, I mean, the general thing would be that if I have an n-level system, a Hamiltonian with an n-level system, then I can expand it in the SUN basis, the SUN generators, which are what you wrote, this Hermitian unitaries, right? And then you are saying that you would like to break them down in terms of SU2 generators, like the two-level systems. Essentially, you would like to re-express the n-level system states or Hamiltonian in terms of direct products of two-level system. And if I manage to do this decomposition, I will be able to encode them.
Not quite that.
Okay, so maybe,
what I'm saying is that suppose I give you basically an omega naught over 2 sum over I z I, right? I'm changing this notation to the standard quantum computing notation, plus basically, let's say j sum over I j nearest neighbor, xi xj, you know, with a delta 1 and then a delta 2, you know, yi yj, right? I give you one such model, right? I think if I avoid special points, this is non-integrable, right?
Yeah.
Sorry?
Yeah.
And so now I ask, what is the ground state of this Hamiltonian? Then what I'm basically saying is you don't have to do any more work. The Hamiltonian is already a string of poly words. It actually already appears as a linear combination of unitaries. And so you directly implement it. Now the problem comes if I basically start with basically some fermionic Hamiltonian, and I'm trying to do, let's say, electrons. You know, I'm trying to find, like, write down the lithium atom or whatever, and I have electrons running around, and I really need to pay attention basically to. So I'm in a different, you know, I have to include occupancy or something like that. I just can't deal with spins. I have to deal with full-on fermions. Then in full-on fermions, you need to map it to qubits so that I can do standard quantum computing on circuit model.
Yeah.
Right, and that's another step. So I'm just saying, let's start with just. Let us start that all of the problems that we're interested in. So we are interested in the following ansatz of problems, which is we want to find the ground state of basically spin Hamiltonians, right? So by doing that, Shorin, what I'm doing is I'm already restricting myself to the space of polyspins as tensor product spaces in which the Hamiltonians are constructed. So I'm giving myself a gift. But without this gift also I can work basically.
Yeah, so maybe the question would be that if you have higher spins, will you then, if you have to encode it, will you decompose it into lower spins and then encode it? For example, spin 1s and let's say even larger spin Hamiltonians. Then will you be forced to encode it? Will you be forced to decompose it into smaller spins like spin halves? Right.
So you always have to go down to spin halves because so let me make a point about the way the literature moves on this. So the literature's point of view is quantum computing, you have to hold something constant when you discuss quantum computing, right? So let's say that I simply allow, you know, I want to discuss whether or not basically my Hamiltonian has better susceptibility, you know, my Hamiltonian has better heat capacity than your Hamiltonian, right? Then we have, for these kinds of questions, you have to normalize something underneath, right? And the kind of equivalent question in quantum computing community is, you know, is how many gates are required to implement a given quantum algorithm inside of basically the circuit model.
Yes.
Right, and the circuit model with 1 and 2 qubit gates is the only thing that is allowed. So if you have qubits or if you have 4-level atoms, if you have some complicated Hamiltonian over higher spin problems that you're writing, you have to boil all of them down. So just like with fermionic encoding, you have to encode all of them onto single qubit gates, where all of the physics is reproduced on a single qubit level, and then you have to start from there.
Yeah, so I think, no, thanks a lot. I mean, this is what I was asking, that if it is an SUN, you have to break it down into SU2s, and then you know how to encode them. If I have an n-level system, I must write the Hamiltonian in some effective 2-level system and expand it out, and then I know how to start encoding.
General SUN you can decompose as products of SU2s.
Yes.
And anyway, this decomposition is painful, but it's well known how to do it.
Yes, sure.
And then you basically have to start the conversation from that point of view.
Okay, thanks a lot. I mean, that answers
Sure, no, absolutely. Okay, so the reason that I'm mentioning a linear combination of unitaries is it's a very famous technique that you will see all over the place. And it actually addresses, I think, one of the fundamental questions. So you know, remember what the kind of, let me draw a simple diagram of what these variational quantum algorithms look like. So what the variational quantum algorithms look like are the following. So all of your quantum states have to start with the same initial state, right? So that there is no cheating. involved. And then what you do is you prepare, basically, there is a unitary ansatz which you prepare, u of theta, and I've drawn it over the entire thing, but maybe I should put it in smaller boxes over fewer qubits. And this basically encodes my quantum state and makes it a psi of theta. And then what I need to do is I need to go from here at the end of the day. By the time I come back to the classical feedback loop, I need the expectation value of psi of theta, psi of theta. I need the expectation value of A and psi of theta. So psi of theta now is a physical quantity which exists on these wires. And it depends on how entangling I have made u of theta and what choices of parameters theta I have chosen. Now the question is, what is A? And what I'm saying to you is that A can be implemented as basically, a bunch of boxes basically. And what those boxes do is they enforce basically this thing that we were just talking about. So xi, and maybe this appears for some time delta t, which is proportional to j 1, 2, and delta t 1, 2. And this appears for a time delta t 2, 3, which appears proportional to j 2, 3, so on and so forth. So what happens is that by controlling basically the time or basically equivalently the trotterization and the depth of the circuit, you can basically enforce the amplitude J23 and the corresponding basically unitary you can also implement if you're computing the unitary. But whereas if you want directly the Hamiltonian, this particular thing, what you do is you don't actually get involved in this business. What you do is you just put down the x1, x3, and then maybe the x2, x4. You put down these kinds of terms, and then you compute the expectation value as basically the following. You break this expectation value on a computer, a sum over k, ak times psi theta times uk psi theta. So there is a polynomial number of terms ak, right? So k is in poly. So there is a polynomial number of terms ak that you have to process separately, and for each of those polynomial terms, what you do is you compute this expectation value. So the first time around, you just run this machine with just x1, x3. You measure everything that you want to measure at the end, right? You make all your measurements that you're interested in, and those measurements basically will be the content of basically the discussion before I end for today. That measurement basically tells you the expectation value of this quantum state. Then what you do is you come back. So now you know what psi k u1 psi theta is. Then you come back and you do for u2, you do for u3. After you're done, you can then compose the expectation value and you can take gradients of it as well. So you can move the value of theta by a small amount and take the gradients and so on and so forth. And taking the gradients also, there is a little bit of a trick. There is some shift operator techniques which I have to discuss, but I'll reserve it for the last day along with the Barron Plateau. Okay, because it's not a very important detail for the rest of the discussion. Okay, so with this, I just want to end by basically making an argument. So hopefully what I've convinced you is that I've convinced you of the following statement I'm writing. If I can measure psi theta uk psi theta, I can measure psi theta a psi theta, right? So, so I hopefully have convinced you of this statement, because I don't know how to measure the UK yet, but if I do it, then it's just the linear combination of the answers with the coefficients being given by the expansion coefficient of A. This much I have hopefully convinced you. So what I will just show you, it's quite a simple trick. What I will just show you is how to measure the expectation value. It's in fact quite simple, right? So the question simply is how to compute, how to measure psi theta u psi theta, because I've removed the k basically because I'm just doing it for a generic, but maybe I just leave it alone for a given UK. Right, this is the same question because UK times psi theta is another quantum state. This is the same question as basically asking, how do I measure psi theta phi theta. Sorry, psi times phi. So if I give you two quantum states, psi and phi, how do you measure psi and phi? And in fact, it's even more restrictive than that typically. Typically, what you're interested in is actually the expectation, just the absolute value. But this is not very important. I can show you that if you can calculate the absolute value, then you can calculate the other quantity as well. Okay. So let me just briefly tell you one thing, and a variant of it is the one that allows you to measure it. So let me just present the circuit to you. So suppose I take a quantum state. Let me just draw the following circuit. Suppose I take a quantum state which is 0, and then what I do is I perform a Hadamard transform on it. And then I controlled on it, I basically perform, I'll call this the permutation operator P, and I have two quantum states, psi and phi, as inputs. And basically what I do is Hadamard again, and I measure on the Z basis. I want you to consider this circuit just for 1 second. And I'll write down what P is. P acting on I1, I2, I3, so on and so forth, is simply IN, IN, I1, I2, so on and so forth. So this is basically just the right shift operator, basically. All that it does is it just shifts all my qubits to the right. So specifically, basically, if I start with I1, I2, this permutation operator basically just produces I2, I1, basically, right? So it just acts as a swap gate. So so with this, basically, what I can show is that this particular circuit actually has a very interesting output. And so let me show you what that output is. So to do that, what we have to do is, let me just move it backward just so that I can draw some. So let me call this psi and phi. And here, let me just call it the quantum state. Let me just call it R1. Here, after my Hadamard, let me call it R2. Here, after my my shift, let me call it R3. And here, let me call it R4. Right, so let me just work this out, and then I'll perhaps just give as a exercise the generalized one. So what I'm going to show you is I'm going to show you how to measure the absolute value psi phi squared, and then this component just emerges as an exercise with a little bit of work, basically. So it's not that much difficult to extract it. Okay, so let me just calculate. So what is R1? R1 is just the input state. It's 0, psi, and phi. And what is R2? R2 is just the Hadamard. So the Hadamard has, remember, the Hadamard on 0 takes you to 0 plus 1 over square root 2, which I will call plus. And on 1, it takes you to 0 minus 1 over square root 2, which I call minus. Right? So R2 basically is simply plus psi phi, right? Which I can write as 0 psi phi plus 1 psi phi over square root 2. And then what I do with R3 is a partial swap. So it's a swap, but controlled by the upper qubit. So what this control basically means is that when this qubit is 1, it does this operation. When it's 0, it doesn't. So what does R3 do? On the 0 subspace, it does nothing. It's just psi phi. But on the 1 subspace, what it does is it produces phi and psi divided by square root 2. And now what does R4 do? R4 is basically just mixes the Hadamard. So it takes 0 to 0 plus 1 over square root 2. So it takes it to plus psi phi plus minus phi psi, and divided by 2, because I put 2 here because there's 1 over square root 2 each time. But I can combine this, and I can write it as 0, because plus, remember, is 0 plus 1 over square root 2. So I can write it as 0 times psi phi plus phi psi, right, over 2, plus 1 times psi phi minus phi psi over 2. And now if you measure the probability of seeing 0 is just related to the mod square of this, and the probability of seeing 1 is related to the mod square of this, which gives you the interference terms that you're looking for between psi and phi. Psi phi mod square is just sitting in the probability of 0 and 1. Right? So this is basically called the Hadamard test, basically because you apply at different Hadamard gates here and here. Okay. Okay. So I'm at 4:10, and I want to leave time for discussion. So I just want to end by making just one quick physics analogy for those of us who've done BSc in physics and so on and so forth, and also those of you who are interested in interferometry. So if you've seen basically any interferometer, right? So it basically looks something like this. So there is a mirror over here, right? There is a mirror on the far end over here, and then maybe I send light like this, right? So I send a 0. What does a 0? I call this line 0. Every time I see a beam splitter, I change notation, right? So what does the beam splitter do? It sends some light like this and some light like this. But what is this? This is just 0 and 1. It goes to 0 and 1. And then what happens to the light when it goes to 0? It gets reflected and it comes back here, and it gets reflected and comes back here. And it re-meets over here and maybe goes over here where you can measure it, right? So this is basically just the Michelson interferometer. This is an example of applying a Hadamard transform. So what Hadamard does is it splits 0 to 0 plus 1 over square root 2. That's basically the exact same thing as taking this path, so this forward path of 0 plus 1 over square root 2. That's the first Hadamard transform. And then what happens is that once they return back, I'm actually doing another version of it as well, right? So when I see it in the detector, it's basically coming from 2 different sources, right, which are interfering with each other. And that's the second Hadamard transform. The second Hadamard transform combines the 2, and then you finally measure it. So what this little upper diagram here that you will see often in quantum computing literature, what this is it's just an abstract representation of what a simple interferometer is. And it's well known to us what interferometers do. Interferometers change amplitudes to intensities, phases to intensities, and they allow you to measure phases. So in exactly the same way, basically what this is it's a machine that combines basically a permutational shift operator, which is like a swap. So it partially swaps 2 quantum states and then interferes them and measures basically what the overlap is. So that's the way in which you can measure the overlap of quantum states inside a quantum computer. And this overlap is of course related to the linear combination of unitary expectation value, as I just pointed out, for the reasons that I pointed out. Because expectation value of an operator A inside the LCO ansatz can be thought of as just a linear combination of coefficients AK combined with the expectation value U inside of psi, which is just the amplitude, the complex part whose mod square is the one that I just showed you how to calculate. Right? So how to do the complex part is just a little bit more algebra, but you're convinced basically that we're in the neighborhood of what we're doing, and so we can basically work out the rest of it as well. Okay, so let me just also point out just one more diagram, which is another alternative interferometer, which also shows this. It's an unfolded Michelson interferometer, or a Mach-Zener interferometer. And the Mach-Zener interferometer does the exact same thing. So you send light through one arm. Here is one Hadamard transform. It's a beam splitter. That's a Hadamard. Here is another Hadamard transform. That's another beam splitter. So light has 2 options. It can go from here to arrive at the detector, or it can go basically it can go from here and arrive at the detector, right? And these two parts interfere with each other, and that's exactly how we extracted our information as well. Okay, so let me just stop here. Let me go all the way up and say that, you know, two of these questions are hopefully somewhat answered in your minds right now. I'm happy to take some questions, and then the next lecture, what I'll do is I'll come back, clean up some of this, and then I'll continue on by showing you how to represent psi of theta, talk about system-aware ansatses, hardware-efficient ansatses, why they're important, what the big deal is, and also point out a little bit about how to optimize A and talk about barren plateau problem and basically, you know, that Haar random blah, blah, blah. Okay, so thank you very much. And there are some questions in the chat box already, which I'll try and work through. But Sharon, do you want to?
No, I think first of all, thanks a lot.
No, my pleasure entirely.
Wonderful talk. Also, this end session, which was hands-on, kind of, yeah, one could just follow you and work out, you know, parallelly. If you wish, you can just go to the chat box and look at the questions, or I can also pick for you. I mean, I'm comfortable.
Yeah, so I have some. How variational quantum circuits play a major role in machine learning, especially quantum machine learning. So yeah, so Tamal has asked this question. So this is exactly the way, Tamal, what I wanted to do was reserve that for a kind of later discussion. I mean, so I very purposefully did not say anything machine learning oriented in the title of my talks because I didn't want to draw unnecessary attention, so to speak. But really the point is that what these kinds of tasks allow you to do is compute expectation values and run optimization algorithms. And you can see how machine learning is essentially a generalization of the optimization program. So in physics, we learn gradient optimization, and we learn basically, we learn how to do optimization over proper functions, over function spaces. And then if you kind of generalize a little bit to computer science and so on and so forth, then they'll even tell you how to think about optimizing over discrete sets and so on and so forth, things of that sort. And this is related to kind of algorithmic searching problems and so on and so forth. And so Grover's search is actually an example of that universe of problems that we're interested in. And so once you're in that category, you can understand very quickly how, you know, machine learning is just another example of, you know, hey, optimize the kind of plane that separates all cat pictures from all dog pictures in my training set. This is just another, you're just asking a kind of complicated version of an optimization question. Yeah, I'm underselling machine learning by quite a bit. It's a very technically terse field, but I don't know much about it except for the tiny bit that I do. Yeah. Okay, so let me go to the next question. If someone has no experience in the field but is interested in learning, how should we start? I mean, what materials? Yeah, so what I would say is basically that I think you need a good foundation on a good quantum mechanics course and a good quantum computing course, and you know, and wherever you are, I'm sure that these are available around the country now, and so you can go through that. If you're in an institute like IISER, then of course, you know, you're you know, my teachers are your friends and are your teachers, and so please ask them, and you know, and they'll guide you to it. But otherwise, if you're outside, the National Knowledge Network, I think, has a course by Anil Shahji, which is available. So you know, we can talk. Yeah. So there are methods for you to kind of get all of this that you're interested in. Is it so? Shubhrajit Pal asks, is it the same problem? Like for any psi, we can find a unitary that results phi. So I'm not entirely sure, Shubhrajit, what you're asking, but I think this is what you're asking. You're saying if I give you a psi and I give you a unitary u, can I always just call it a phi? If u is a unitary transformation acting on a quantum state, then it is another legitimate quantum state in the Hilbert space. So basically, the problem of estimating psi u psi simply boils down to the problem of estimating psi with phi. This is the same problem, basically. And so this is why I can simply ignore the fact that there is a unitary transformation. You've applied it already. And so I just, I can just imagine that to be the case. Yeah. What are x1, x2, x3, x4 in the previous circuit? Sorry, this is time-stamped information. Sorry, can this person, Madhurima Das, can I please ask you if you meant these quantities, R1, R2, R3, or did you mean x1? What x1 are you talking about?
Madhurima, are you there? Can you just unmute yourself?
Oh, this x1, x2, x3. Sorry, these are Pauli operators, Madhurima. My bad. Sigma x is the same as x.
Sir, how do we define those Pauli operators?
Sorry, yes, okay. So this is part of a fundamental quantum mechanics course that you should definitely walk through. So the Pauli sigma x is basically just 0, 1, 1, 0. The Pauli sigma y is 0, minus I, 0. And the Pauli sigma z is 1, 0, 0, minus 1. And along with the identity operator, which is 1, 0, 0, 1, it's a basis for all 2 by 2 matrices. Right? And the additional feature that you have is that all 4 of these are Hermitian unities. Right? And all 3 of these are traceless. And so they have some fantastic properties and they're used all over the place. This is a workhorse of a basic quantum mechanics 101 course. And so I highly recommend that you should just go for one. Yeah? So this lecture will presumably just be on YouTube. So for those who are basically a little behind on their quantum mechanics experience, you could just run through a quantum mechanics course and you can come back and stare at this. It's not a, it's not a huge problem here. So Prahlad Shenoy is asking, what are unitary transformations and what is a quantum simulation? So a unitary transformation U is a mathematical operator. It's a complex n by n matrix such that U dagger U is the same as U dagger is the same as identity. And so this object is basically what is called a unitary transformation. Right? It comes from basically the fundamental point that quantum states basically preserve norm. So if I have a fundamental quantum state psi, and then this quantity has to be 1, and this quantity has to be 1. And basically what this means is that if I transform psi with some linear transformation, if I transform it to another vector phi, phi is transformed to psi, then what I can do is I have to argue with you about Hermitian inner products, blah, blah, blah. But what I can show you, if you work with me for 5 minutes, is that this quantity is the same as m dagger m acting on phi. So this m phi is what I call psi, and now the question is how do I flip it and take an inner product? And now I have to argue something about Hermitian inner products to you, and that promotes basically this inner product. And the moment you take those inner product, what has to happen is that this has to be equal to 1, but on the other hand, this is also a valid quantum state. So, so this has to also be equal to phi phi. And so the only choice, because I haven't told you what phi is, the only choice is m dagger m is the identity operator, or m dagger is the identity operator, which is the same thing as this quantity that I've just written. Right? How accurately variable quantum algorithm plays a role in eradicating error in quantum circuits? I don't fully understand what this question is. Sushma, do you want to be more specific about it? Oh, I missed a couple of questions beforehand, but Sushma, go ahead.
Shai, it's okay, you can move ahead. It's
okay.
Fine. I mean, yeah.
Okay,
yeah.
it's fine. So another person has asked, Aditya Mishra has asked how to optimize expectation values, for example, on photonic quantum computers. Exactly this way, Aditya. So what you do is you have this kind of a thing. What I've just told you at the end of today is how to estimate this expectation value. And now what you can do is this expectation value is just some real number, right? It's some f of theta. And you can run a gradient search algorithm on it. For instance, you can just run a first order variation and run a gradient search algorithm on it. And so basically what you can do is at 2 values of theta, you compute f, and then you compute the gradient and you just climb, you hill climb basically. So just standard classical optimization. There's nothing more attached to the optimization bit, which is why I didn't bother to talk about it. properties of molecule that make it feasible for this ground state optimization technique? Dadi Kamlesh is asking. So Kamlesh, this is a fantastic question. This actually is a complicated question. So let me just say this off the bat. The reason for it is basically when you have real molecules, typically what you have to do is you have to encode from the fermionic space, the Hamiltonian that you have to encode it onto qubits. And when you encode fermions onto qubits, you have to actually pay attention to Pauli's exclusion principle and whether or not you're encoding basically you have to encode two pieces of information basically. One is the occupancy and the other is the spin flip basically information. And both of these for you to, so there are different encodings to do this and so on and so forth. So this gets really, really complicated. So I can point you towards references where several different molecules have been considered and the number of qubits that are needed to optimize and get their ground states are explained. But let me try to give you a heuristic answer, a qualitative and very bad answer. So my limited understanding of reading the literature a little bit is basically that people can do small molecules like this, LIH or something like that, they can do small molecules they can do. But if you go to the simplest kind of chemistry problem that we considered in quantum chemistry problem that we considered in high school, like something like benzene, you're already dead in the water. Already people cannot do it anytime close to now with good quantum computing. They cannot find ground states of it because there's just too many electrons running around for them to kind of be able to do justice to this. So there are some real nice papers on this where they actually tell you and so there is also this ansatz encoding dependence basically. So whether you use basically the Jordan-Wigner ansatz or whether you use the Brevet-Kitev ansatz, and so depending on which ansatzes you use, the number of qubits that are involved slightly change up and down and so on and so forth. So there is some blah, blah, blah to this that you have to look up, yeah? Okay, so there are no more questions here which are, I think, directly relevant. So there is one last thing that I'll just take up, which Nabia Iqbal is basically asking, hey, what do you mean by the word ansatz? Sorry, Nabia, I should have maybe mentioned this beforehand. So an ansatz is just basically an assumption of how my wave function looks. So if I say that my wave function basically let's say two electron problem, my wave function looks like alpha up down plus beta down up. I am basically saying, what I'm actually saying is, it never looks like alpha up up plus beta down down. I'm just saying it never looks like this. So the moment I basically write something like this down, these are local unitaries, so it would be silly in quantum computing context, but let me say I'm not allowing local unitaries also. I only allow you this. So the moment I say something like this, I'm already kind of I'm making a prediction on what my unknown quantum state's form looks like. So this is what an ansatz is, basically. And so you can make an ansatz for what your Hamiltonian looks like. So a Hamiltonian ansatz is basically saying my operator A always looks like sum over AK times UK. Who told me that this is true? Maybe this is never true, right? This is always true if you basically make an approximate Pauli encoding, qubit encoding, because Pauli operators are a good tensor product qubit basis. So this is almost always true, unless you basically insist to stay outside of qubit basis, which is in uninteresting ways. So the linear combination of unitaries argument is basically just a fairly sound argument, but it is a choice technically, and that is why I kept calling it an ansatz. Okay, so can I just hand over back to you, Sharon? So
yeah. Thanks a lot for patiently, answering.
No, I'm happy to kind of continue around, but I think there's another talk at 4:30.
Yes, we are almost there. I think we still have a few minutes left. Any other question? If somebody wants to unmute and ask. We have to wrap it up in a few minutes, but there are still last few minutes.
Anyway, Sai will come again. So by popular demand, because Sai is my demand also. Because
yes, no, my pleasure.
Perfect. Okay, so fine. So I think we just finish here. Sai, thanks a lot again, and I hand it over to Prashant.
Thank you.
Okay, thank you very much, Prashant. Thank you, Sharon. Bye-bye, everyone.
Bye.
Bye. Bye-bye.
Now, Sovereign Alok will take over.
Yeah, absolutely.
Hi, Surin.
Hey.
Hi, how are you?
Yeah, I'm good. How are you?
Yeah, I'm fine. Just managing the things in this COVID.
Yeah.
This guy is good, yeah? Sorry, name.
Yeah.
Very clear, actually.
Yes.
Hi, Cyril.
And this development of, I think, using iPads directly for lectures have been very good. I think this has really added, when you're online, it has really added something to it. Okay,
So
I think our speaker is here.
Speaker has joined, yeah.
Yeah, hi everyone.
Hi.
Hi. How are you, Cyril?
I'm good. How are you?
Yeah, I'm fine. Is everything fine there?
Yeah, a bit complicated with
Yeah,
doing this,
yeah,
but
yeah.
it's going fine.
So you got vaccine?
Yeah, I got my first shot
First shot, okay.
2 weeks ago.
Good. Weeks ago.
How about you?
Yeah, I got the first dose and I had COVID, that's both
that's
together.
right.
So I already had both the vaccines. Natural one and the...
Did you fully recover?
I'm sorry?
Did you fully recover?
Yeah, I think so. I had some weakness, but I think I have. Yeah.
How's your family?
Our family is fine. And how is the Anne and the kids? They're good.
Yeah, they're good. Yeah, full of energy.
Yeah, I still remember this. I met Izia that last time.
Yeah, that's right. Yeah.
So, Professor Panikkar, should we start?
Yeah, please start.
Or maybe let's wait for 1-2 minutes because it's 27. Maybe it's some more people will join, right? Some more people will join. So, Cyril, we have some restriction in the Zoom. So there are some in the Zoom platform. We have some participants, but most of the participants are there in the YouTube channel because we cannot accommodate all of them, and it's a kind of privileged one. That is, those are here in the Zoom platform. So, but because there are around 15,000 registered students, I don't think they all will come, but around 700 students or 1,000 students they come usually. So the YouTube platform they are
really big.
Yeah, and it is the live in the YouTube.
So how do you get the questions?
Yeah, the questions, one thing is that you can read from the Zoom platform or I can read it for you. And the YouTube case, I will read it for you.
Okay.
And normally we have a lot of questions, but you have 30 minutes to respond. Yeah, that's all. I found the last week your PRL, the elegant joint measurement one. That's very interesting, very nice. Yeah. We are following that paper. Maybe we have not read completely, but we're trying to read this.
Yeah, I'm not to talk about it anymore.
Yeah, I know. Yeah. We'll be talking something else today. Yeah. So let's wait 1 minute and then we'll start. Yeah, it's 29. We can start. Professor Panikkar?
Yes, you can start, not a problem. Start.
Yeah, we can start, right? So, yeah, we can start. So, welcome to this session. And good afternoon to the participant, and once again, good afternoon to the speakers, Dr. Cyril Banksiard. It is indeed our great pleasure to have Cyril with us today, and we thank him very much for accepting our invitation. Dr. Banksiard is currently a professor at Institute of Neil, a CNRS institute like our CSIR and DST institute. He did his PhD from University of Geneva with the great Professor Nicolas Gissa in 2009, and did his postdoc from 2010 to 2014 at Griffith University, Australia with Professor Gerard Milburn. Dr. Banksiard is actually one of the very few young researchers, truly, and who has received such a wide recognition in the field of quantum information theory and quantum foundations. He is truly renowned in our field of research and has made quite a number of pioneering contributions, starting from this crypto non-locality, error disturbance relation, quantum network, and many more. I personally believe that his single author paper that is on error disturbance state of relation back in 2014 that was published in PNAS, and that actually earned him a wide appreciation and a respect in the field. He's a theorist, but he has a strong interest in the experimental collaborations, and he did, in fact, many collaborations with the experimental group. And quite a number of his theoretical proposals have already been tested experimentally. And he has published around 16 research articles in the high impact factor journals. For example, Nature, Nature Physics, Nature Communication, PRX, PRL, PNS, Science Advance, and many more. In fact, as I mentioned that he published, last week he published a PRL on quantum networks, actually a very interesting paper. Today we got the opportunity to listen to him, and he will be talking about the indefinite causal order, and it's a very interesting and important topic. So therefore I request students to listen him carefully and ask questions in the chat box, either in the Zoom platform or in the YouTube channel. So with this, I would like to invite Dr. Cyril Bansiard to deliver this lecture. Thank you.
All right, thank you very much, Alec, for the introduction. I think that's the longest and kindest introduction I've ever had. Thank you. Should I start sharing my screen? Yeah. So thanks also to the organizers for inviting me to talk and to be part of this this summer school. I'm very happy to be part of it, and I'm actually very honored, given the list of speakers that I saw on the website. I'm very honored to be part of it. So for this lecture, I decided to talk about the subject that I've been working on in the last few years, and that I find very exciting, and which is quantum indefinite causal relations. So in general, the reason why I'm excited and I like to work with quantum theory and quantum foundations, quantum information, is because it's a very weird theory. It's very counterintuitive. There are many things that defy our common classical intuitions. And in some sense, this idea of indefinite causal relations, to me, takes this to the next level, and this is why I find it very fascinating. This has become quite an active field of research in the last decade or so. So in this lecture, I will not be able to give you a full review of this area of research, of course, but I will try to give you some idea of the kind of questions that we are looking at, the kind of framework that we are working with, and the kind of thing that we try to do in the subject of indefinite causal relations. Also, I will not go too deeply into the technical details, and there will still be a few equations. In any case, if you have any questions, I'm happy to take them during the lecture or afterwards. But yeah, please don't hesitate to interrupt me. That's perfectly fine. Right, so what I'm talking about, causal relations. What do we mean by this? And in this study of indefinite causal relations, what is the kind of scenario that we are looking at? So this is the general setup that we typically consider. We have two boxes here, A and B, that you can see as two parties, Alice and Bob. And they will perform some operations that will define some events. So what I mean is that, so you can see A and B as being in some closed laboratories. At some point, At some point, they open their laboratory, they receive some physical system, and they can perform some operations. So they have a choice of possible operation, which I denote by X here, and they may get some measurement outcome, A. And then they send out some system. And of course, same for Bob. We're looking at the relations between those events. So the events are just what I just described. So something in the lab, you choose a measurement to perform, you get some outcome, and you send something out. These are the events that we consider, and then we are looking at the correlations. So the correlations are described as is usual in quantum information. We like to study this kind of object. The correlation described by the probability distribution of getting outputs A, B conditioned, and the inputs X and Y. So in the field of quantum information and quantum foundations, this is an object that appears very often. And if you are familiar with the study of quantum non-locality, that's typically what we're looking at. We're looking at those correlations, and we ask whether there can be a local model. So here I will not ask about locality, but instead I will ask whether those events that I defined can be embedded in some well-defined causal structure. So I will look at the causal relation between those events. What I mean by this concept of causality is in terms of influence. So I will say that there can be a well-defined causal structure if, in this case, if Alice comes first and then comes Bob, and it could be that A influences B, but since B is in the future, then it shouldn't be the case that B influences A. So you can have only some one-way influence, some one-way signaling. Or of course, vice versa, if I have a well-defined causal relation where B comes first and then A. So that's essentially the question that we're asking. Can we say that those correlations are produced in some according to some well-defined causal structure in this sense? And I will just clarify already that we will be looking at this question at two different levels. And the first one is precisely what I just described. By just looking at these probability distributions between inputs and outputs at the fully operational level, where you just have access to those classical inputs and outputs. And this is a fully theory or device-independent theory, independent approach. Okay, this is also a terminology that we use a lot in quantum information and quantum foundations. That's one approach. And the other one is theory or device dependent. So what I mean by this is that those events that I described before, at A or B places, they should be described by some given theory. So of course, here in the context of this talk, I will talk about quantum theory. So I will say that, okay, we should have a quantum description for those events. What that means, well, in quantum theory, we say that physical systems live in some Hilbert spaces. So I should be able to attach some input Hilbert space to what's coming in, some output Hilbert space to what's going on out. And then the general operation that can be performed according to quantum theory is what is called a CP map, a completely positive map. I will come back to that. I will describe it in a bit more details. But essentially, here at this level of the description, I trust that I have some input-output Hilbert spaces, and I trust that A and B are performing some given quantum operations. All right, so this is the general setting. In both cases, theory device independent or theory or device dependent. I'm asking whether those events can be embedded in a well-defined causal structure. And as you can guess from the title, we will see, I will argue that in some cases, you cannot talk about a well-defined causal structure. All right, so of course, that was the same for me. So here's the outline. I will present in more details those two approaches. In the first case, I will introduce the notions of causal or non-causal correlations and causal inequalities. In the second case, we will talk about causal non-separability or causal witnesses. And this will be the introduction of the main concepts that we use in this field, or at least in one approach to the field. Then I will come back to more practical scenarios that you can find in the quantum world, which is the quantum switch. And I will tell you that we can have some applications of these fundamental ideas. And if time permits, I will tell you some more about generalizations of this quantum switch, so other types of quantum circuits with indefinite causal orders, and maybe if we have really enough time, I will talk about some of the latest research project that I've been working on, where we want to have a fully device-independent verification of indefinite causal orders in the lab. So let's start with the first one. This is again the scenario that we're looking at. Here again we're looking at just the correlations. A, B, X, Y are classical inputs and outputs. We don't know what's happening inside the boxes. And so again, the causality constraints are that there should only be some influence in one direction. So I would say that, okay, we can define some fixed order if Alice can signal to Bob, but not vice versa. So the way this translates in equations onto this probability distribution that we are looking at is that if I'm only looking at what's happening on Alice's side, so I'm looking at the marginal probability distribution of Alice. I forget about what's happening on Bob's side, so I sum over his outputs. Well, what's happening at Alice shouldn't depend on what's going on in the future on in Bob's laboratory. So here, this probability of observing A shouldn't depend on Y, Bob's input. So we have this constraint that those correlations that have a fixed causal order from A to B have to satisfy. And of course, vice versa, if we have a fixed order where B comes first, this is what this means. Well, if I only look at the marginal probability distribution for Bob, this shouldn't depend on X. So we should have this kind of constraint here. So these are constraints that you can check at the level of the probability distribution. If this is the case, then the probability that you observe is compatible with a fixed order where A comes before B. If this is the case, where it's compatible with a fixed order where B comes before A. Then in that seminal paper by Oreshkov, Kost, and Bruckner, they propose to consider also the situation where you can have a classical mixture of those two cases. So that means essentially that there is, every time you repeat the whole experiment, then there is some causal order, but maybe you don't know it, so it comes with some, or maybe it's just probabilistic, so in some cases it's A before Bob, A before B, in some cases it's B before A, with some probabilities. And in that paper, they argue that this kind of correlations, if you observe such a probability distribution, then you should still say that this is compatible with a well-defined causal structure. So they propose to call these causal correlations. Essentially, any correlation that you observe that you are able to decompose in this way will be causal, will have a well-defined causal order, whether you know it, whether it's fixed or probabilistic, but still it's somehow, it's really not surprising. All right, so that was the proposal by Oreshkov, Kost, and Bruckner to call these causal correlations and to study this. So how do we study these kind of correlations? Well, okay, before this, maybe I will give you a concrete example of such a correlation. So suppose you observe a correlation as this one. So all inputs and outputs are bits. The inputs are random bits, so 0 or 1 with equal probability. And you observe this correlation, so with the Kronecker delta. So that means every time you do the experiment, you observe that A is equal to 0, B is equal to X. So B here is equal to Alice's input. Is this causal? So can you explain this kind of correlation by referring to some causal background structure? Well, clearly, yes. Clearly, this is causal because, okay, Alice just has to output 0. This is very easy to do for Alice. And then Bob has to guess Alice's input. But Alice could simply send her input through this communication channel to Bob. Since she is in the past, she can send some information to Bob. So she can just send her input and Bob outputs what he receives. So it's perfectly fine. This is causal. They can perfectly get these correlations in a causal manner. So let's change a little bit this example, and now I will ask. I cannot. Right. Now I'm asking that still Bob guesses Alice's input, but I'm asking that Alice also guesses Bob's input. So Alice's output, A, should be equal to Bob's input, Y, right? And still Bob's output, B, should be equal to Alice's input, X. I'm asking you again, is this causal? Well, as we saw before, this is fine in this situation for Bob to guess as Alice's input, because she can send it to him. But clearly, if this is the causal structure behind, if Alice is in the past of Bob, sorry, then clearly Alice cannot guess Bob's input, which will be given to him in the future. And if this is random, well, there's no way for her to always guess his input. So this is not causal. And in fact, you can show that for causal correlations, any correlation of this form, the probability of success to this game, so that the probability that indeed you reach, you get that Alice's input is equal to Alice's output is equal to Bob's input, and vice versa. This probability of success is upper bounded by 3/4. That's fairly easy to see if this is the situation where A is before Bob. Clearly, by symmetry, it's the same if Bob is before Alice, and then if you mix the two, you still get this band of 3/4. So what this means is that this assumption of causal correlations, of causality for correlations, that puts you some bounds on what kind of correlations can be observed. And this is, again, very similar to the case of non-locality. The assumption that a probability distribution has a local model gives you some bound in terms of Bell inequalities, some bound on the correlations that you can observe. And this is what was called the causal inequality in that paper by Costa and Bruckner. All right, so how do we study now? How do we go beyond this example and study causal correlations? Again, we use the analogy with Bell inequalities and the local correlations. So I will go very quickly and present the general way to study correlations as we do in the Bell scenario, and show that this is pretty much the same in this scenario. So what we like to do when studying this kind of correlations, for a given scenario where we have a given number of inputs and outputs, this whole correlation can be written as a vector. So we just list all the probabilities for each combination of inputs and outputs. So you get a point or a vector in a large dimensional space. So for instance, if you have a binary inputs and outputs, here you get 16 probabilities. You define a vector in a 16-dimensional space. And then the set of causal or local correlations is just the set of all points in this large space. And typically this will form what we call a polytope. A polytope is some high-dimensional object, which is the extension of a polyhedra. So essentially, a volume in this large dimensional space with a finite number of vertices and a finite number of faces. So if we do it, then we can define this set of correlations that are compatible with A coming before B. And again, this is all the correlations where we find that the marginal of A doesn't depend on Y. You can do the same for the set of correlations where B comes before A, so where the marginal of B doesn't depend on X. And by definition, these causal correlations are just the convex combinations of those two types of correlations. Just take the convex hull of those polytopes and you get what we call the causal polytope. So in this high dimensional space where we encoded all our probabilities, we get this object, this volume in this space inside which all the causal correlations are. And it's possible, in principle at least, to characterize this volume. Essentially, the vertices are typically the deterministic causal strategies. So we can list them, and then we can take the convex hull of all this. So once we have characterized this polytope, well, we can look at the facets. And this is also what we do with, in the case of Bell local correlations. We look at the facets and what do we learn. So, sorry, I just have a problem. I cannot see my screen anymore. I've done something wrong. And be back. Yeah. So if you look at the facets of the polytope, well, that defines the limits of those correlations that are causal. And the facets, in this sense, define causal inequalities. So causal inequalities are telling us that all causal correlations should be, in this case, below this facet. So the causal inequality that I showed before, this one can be seen as a facet of this causal polytope. So in this large dimensional space, we have characterized all the causal correlations. Of course, there are something outside of this causal polytope. What are these? Well, these are the non-causal correlations, like the one I was giving you as an example just before, where Alice and Bob could both guess each other's input. And this is where we find some indefinite causal relations. So probabilities or causal relations that cannot be embedded into some fixed or well-defined causal structure. And this is the type of correlations that we study in this field, just like we study non-local correlations in the case of Bell non-locality. All right, that was the quick overview for the theory or device-independent approach, where we just look at the correlations. I will just say briefly that this can be generalized to multipartite scenarios, where we have several of these parties, and I will go quick. A naive way to generalize this definition would just be to take the convex combination of all fixed orders. But this is not quite satisfying because we would like to also allow for what we call dynamical order, where the order of subsequent parties could depend on what's happening here. So A could determine the order of what's happening after her, of whether the signal is sent to B first or C, and then or to C first and then B. So in that case, we need to work a little bit more on the definition. And what we do is we take a recursive definition where we say that, okay, it's causal. You can embed it in a well-defined causal structure if, well, you can identify some party coming first, and then condition on what this party does, then all the rest should remain causal. So we have a recursive definition in the multipartite case, but essentially, once you have this definition, then you can characterize the causal correlations in pretty much the same way as you do in the bipartite case. So you also define some polytopes and you look at the facets. It's getting very big, so it's hard to do it even numerically, but in principle, this is doable. You can come up with causal inequalities. All right, so that was for this device-independent or theory-independent approach. Let's move to theory-dependent. So let's introduce some quantum ingredients. So as I said, now we will look into what's happening inside the boxes, and we will assume that what is inside the boxes is described by quantum theory. So again, we have some input and output Hilbert spaces, and some quantum operation, which should be a CP map. So what is it exactly? So the general operation that A and B can do is actually not just a CP map. They have to choose a quantum instrument. But it's a set of completely positive maps that sum up to a trace preserving map. So as you know, quantum theory is probabilistic, so they cannot always choose a deterministic operation. They have to choose several options. And so they have to choose among a set of different possible operations. So for those who are not familiar with that, completely positive, so a map is an operation, a function that takes some operator inside this Hilbert space onto some other operator in this Hilbert space. So typically this will take a density matrix, a quantum state described as a density matrix, into another density matrix. It's positive if any input operator here, whenever the input operator is positive, then the output operator should also be positive. This is what this means, positive. And it's completely positive when you can apply this operation onto only part of an entangled state, for instance, and this remains positive. So these are really the general operations that are allowed by quantum theory. Okay, so this is now how we describe our events. And again, we're looking at this correlation and still ask the same question, whether we can embed what's happening here in a well-defined causal structure. So let me give some examples in the quantum case. So say that Alice and Bob are just given some part of a shared state. So in this case, you have a bipartite state that is sent to Alice and to Bob. What Alice and Bob can do, then they will choose some measurement to perform. So here, instead of just of an instrument, it will just reduce to a P of EM, the choice of an operation, a generalized operation. It could be more general than projective operations. It's a P of EM in general. And then this probability distribution, as many of you should know, this is given by the Born rule. So here you have the operators that describe the P of EM, and here the quantum state. So that's one example. Another example is a channel. So suppose here I sense a quantum state, rho x, so it could depend on the input x, for instance. And there's a quantum channel from A to B, so that Bob receives the result of the channel that is sent to him. Okay, and if I look at the probability, so here I didn't put any output for A, so I just have the probability of Bob, given that he sent rho x, that Alice sent rho x, and that he shows a P of EM labeled by Y, then this is again the Born rule. You apply Bob's measurement operator to the output of the channel. Okay. And it turns out that you can also write this in this form, where you separate what's happening on Alice's side and on Bob's side from what's in between. Okay. And technically, this is done by using what we call the Choi-Jamelkovsky isomorphism. Okay. So here, what you need to remember is that I wrote this formula in pretty much the same way as this one, where I separate what's on Alice and Bob's labs from the outside. And because I'm using this Choi-Jamelkovsky, and because this is a summer school, I thought I would just open a parenthesis. This is something that is very much used in quantum information, and if you haven't learned about it, then I really encourage you to learn about it if you want to work in quantum information. Essentially, this is an isomorphism that allows you to represent any map So here a map is a function again from operators acting on some Hilbert space to some operators acting on some other Hilbert space. So this isomorphism allows you to represent any such map as a matrix now that lives in the tensor product of the input and output Hilbert spaces. This is super useful in quantum information because it's much easier to manipulate matrices than maps. Okay, and there's also the very nice property that this map is completely positive. So this is the property that I described before, if and only if this matrix is a semi-definite positive. This is really very, very useful characterization of CP maps. And also you can show that the constraint that M should be trace preserving also has a very nice representation in this using this isomorphism. So that was a parenthesis. That's an isomorphism. That's a tool that we use a lot in quantum information, and really a lot in this in the framework that I'm describing here. Okay. So again, that was the two examples that I gave, and in those two examples, there was a clear, well-defined causal structure. So in the first one, the quantum state was sent to A and B, which acted independently. There was no direct causal relation between A and B. In the second one, there was clearly a causal connection through this channel from A to B. These are well-defined causal relations that you can encounter in standard quantum mechanics. And then you can ask, okay, in this general situation, where I have those quantum events, can I try to get rid of this background causal structure? And what is the most general way to connect the quantum operations of Alice and of Bob here? And actually, this kind of a formula generalizes fairly easily. And you can show, well, these people showed, Oreshkov, Costa, and Bruckner, again, the same seminal paper. They showed that the most general way to relate some quantum events in this way is through this generalized Born rule. So again, a Born rule that looks very much the same as those ones. So where we identify Alice and Bose operations on one side and some other quantum object here that I denoted W. Here that was the state, here that was the channel, and here we have some more general object W. So this is really the basics of the framework. And this W is called the process matrix. So just to say a bit more about this formula, which is really essential in the whole formalism of process matrices. So here again, these are the actions of A and B. So again, using this Choi isomorphism, so I described these as matrices in these tensor product Hilbert spaces. And here the process matrix is something that connects somehow the operations of A and B. The process matrix connects these operations in a very general way. So I didn't say anything about how these are related. This is just the most general way to write the probability is to introduce some mathematical object, W, that somehow relates it. And that lives in this tensor product of all the spaces that have a role to play here. And just for the record, you will see in the literature that we say this is a supermap, because essentially that defines a function of maps. These two are Choi matrices that describe CP maps. So these are already functions that take some input state to an output state, for instance. These are maps. And this W defines a supermap in the sense that it's a function of maps, a map of maps. Okay, so again, I didn't assume anything about how these are connected. This is a general formula. And in fact, if you look at the literature, a very common way to represent this W, this schematically is this. You will see that if you look at some papers on the subject. But essentially, this means that this W includes everything in the outside world of Alice and Bob. All right.
Can I ask a question here?
Yeah, sure.
Does the CPTP divisibility plays a role here? Because if you have a notion of flow of time, for example, through which usually we connect to causality, we would imagine that it is continuously flowing in time in some sense, and then the CPTP divisibility kind of comes in a particular kind of description. So here that's not important, is it? If it's CPTP?
No. So we don't take this into account. So we only look at Alice and Bob's operations in terms of CP maps, whatever the CP map is. We allow any CP map, and then we see how we could possibly connect CP maps.
I see. Okay. Thank you.
Thanks for the question. All right. So again, this W represents everything that's outside of A and B's laboratories, and that's the general way to connect these. And in the previous examples, I was considering, for instance, a case where this was a channel. So this can be included as a particular case of a process matrix. So either in this direction or in this direction. So essentially, you can check by looking at this W matrix. You can check if it's compatible with A before B or with B before A. So when you look at the structure of the W that you consider, you can see if it allows for some signaling. In this case, this wouldn't allow for signaling from A to B. So in this case, we would say, okay, it's compatible with B before A. And in the same way as we defined causal correlations, then we can define some similar object at the level of process matrices. So we ask whether a process matrix can be written as a convex combination of a process matrix with A before B, so a channel from A to B, and B before A. And this is what was called in that paper causally separable. What this means is that any process matrix, so if you characterize this process matrix that gives you the quantum correlations in this way, if you can write the process matrix in this way, this will mean that somehow there is a well-defined causal order, either A before B or B before A, or maybe some random mixture. Sometimes it's A before B, sometimes it's B before A, with some probability. But still, it's not very exotic. There's always some well-defined causal structure. And you can always relate those two quantum events and embed them in some definite causal structure. Of course, what's interesting is that this formalism allows also for process matrices that are not of this form. And these are the causally non-separable process matrices. And these, by a contrario to the causally separable ones, if a process matrix cannot be written in this way, then we will say that it has no well-defined causal order. It corresponds to some indefinite causal structure where you cannot relate your quantum events in terms of signaling in one direction. So this is still very high level, and in fact, in that paper, they only gave one example of such causally non-separable process matrix. It's really just a mathematical construction. So here, these are Pauli matrices. You take there are implicit tensor products. So you can write some matrix. You can verify it's a valid process matrix. So process matrices that need to satisfy some constraints to make sure that the probabilities they define are well defined. So this is a W matrix that is allowed by the formalism, but and that can be shown not to be causally separable. But this is just mathematical construction. It's really not clear what this means physically. Still, the formalism allows, or quantum theory, when you only assume quantum theory locally, that allows for some situations like this with indefinite causal order. How do we check that this has indefinite causal order? Well, we can look at the correlations that they generate. So clearly, if the process matrix is a physical resource that gives you the correlations. If it has a well-defined causal order, or if it's causally separable, then clearly the correlations that you will get using this generalized Born formula will be causal in the sense that as we defined them before. But vice versa, if you observe some non-causal correlations, then you can show that this is then you're sure that the process matrix that you started with, that you're using to generate those correlations, is causally non-separable. And the way you observe some non-causal correlations is via the violation of causal inequalities. And indeed, this framework of process matrices allow for some violations of some causal inequalities. And this was essentially the main result from that paper, 2012. So yeah, you can violate some causal inequalities. So that's the causal inequality that I wrote before. The process matrix correlations can give you some value up to 0.82 beyond this 0.75 limit. And you get from this a device-independent certification of causal non-separability. So if you get a violation of this causal inequality, then you know in a device-independent way, because you're testing a causal inequality, that the process matrix was causally non-separable. It had no well-defined causal order. Let me just highlight that it's only some of those causally non-separable process matrices that can violate causal inequalities, and so we need some other tool. So I really don't know what are those drawings, the green drawings that appeared.
Yeah, that's someone has done it. Those students who has done it and just remove this part.
Okay, anyway, just forget about them. They're not part of the slides. Okay, so as I said, we can check causal non-separability of a process matrix via the violation of a causal inequality, but not all process matrices violate the causal inequalities. So we can use another tool to verify causal non-separability. And here I'm taking this opportunity to also remind you how we do it for entanglement. So there is a clear analogy that I will come back to that between entanglement and causal non-separability, just as there was between causal inequalities and Bell inequalities. So a standard way to detect entanglement is via entanglement witnesses. And the basic idea is quite simple. So here I depicted the set of separable states. Okay, and this is a very nice and convex and closed set. And now assume that you have some entangled state that is outside of this set by definition. Well, there is a useful theorem that tells you that since this set is convex and closed, if you're outside, then you can separate there's a way to draw a line between this entangled state and the whole set of separable states. Okay, this is called the separating hyperplane theorem. So it's actually a hyperplane that you can use to cut in half the whole plane. On one side you get the separable states, and on the other side you get the entangled states. Mathematically, this translates into this kind of equations. So S, this hyperplane can be described as an operator. And when you take the scalar product of the trace between this operator and the state that you're looking at, on one side of the hyperplane, it gets negative values. On the other side, it gets positive values. And so you can use this S as an entanglement witness, because if you get a negative value, you are sure that it's not separable. All separable states are on this side, and they will give you a non-negative value. And the very same idea can be used now to define causal witnesses, to check for the causal non-separability of a process matrix. Any causally non-separable process matrix can be separated from the set of separable ones via some hyperplane. What's very nice here, so this is really the same idea as for entanglement witness. What's very nice here, which is not the case for entanglement witness, is that S can be constructed via semi-definite programming, which is, I think you heard about it already in the summer school. That's a very, very common, efficient way to optimize some problems. And once you have constructed a witness, then you can actually measure it. You can perform some experiments on your process matrix, and you combine the statistics and you measure the witness and verify if you get a negative value on that. And that's something that was done experimentally. Okay, I think I need to move quite quickly. I just wanted to say, okay, this can be generalized. This notion of causal non-separability can be generalized in the multipartite case in very much the same way as for causal correlation. So we also have similar kind of recursive definition. There are some subtleties, but I will not have time to go into details. And before moving to the next section of the talk, I just wanted to highlight again this analogy that I mentioned already a few times between Bell non-locality and entanglement on one side, and causality or causal non-separability on the other side. And I want to highlight this because all this on this side about non-local correlations, Bell inequalities, entanglement, this has been studied a lot in the last few decades. So there's a lot that is known. There are many works, many directions that has been suggested to study, to investigate. And so we can really get some inspiration from this. And this is actually how we got the idea to study the causal polytope, to come up with causal witnesses. So the analogy is not really fully formal. It's not mathematical, the same mathematical objects. It's not, but still you can really get some good inspiration. And this is still an analogy that we use a lot to further investigate those ideas of causal or non-causal correlations, or causally non-separable processes.
All right. Can I ask a short question here before you move on? So I think the whole formulation, what I did not see is the presence of an arrow of time, or when you think of arrow of time, we associate a Hamiltonian, and e to the power IHT is what comes to our mind. But when you formulated the whole thing, it was done in a kind of without getting ever into e to the power IHT. The whole discussion. Where is it hidden? Can you hint at where it is hidden? Where I should?
So precisely at some point, and when presenting the problem, I kind of had this question of whether there is a causal structure behind. And when I moved from the two examples of quantum states and quantum channels to general process matrices here, so these lines at the backgrounds, they suggest some maybe space-time structure or causal structure. Mm-hmm. And then I got rid of them precisely because I wanted to get rid of any space-time structure. So I got rid of the arrow of time. Mm-hmm. So in this general formulation, I just don't want to assume any arrow of time. I don't want to assume that there is a global time that it determines what's happening outside of A and B's laboratories.
I see. So
There is still a global.
Is there a sense of causality even without a notion of global sense of time? Are you saying that? So imagine I have a null
So
Hamiltonian.
that's precisely the.
Is that what? Yeah, this is what I want to understand. Exactly. This is very confusing.
That's
very
precisely the
interesting.
question. So here I just remove. So if you do standard quantum theory, there will always be indeed Hamiltonians and an arrow of time. Here I'm just looking at those quantum events, and I try to remove the background structure. So I just remove this arrow of time that would link, in general, the two operations of A and B. Mm-hmm. And I look at the general probabilities that could arise according to quantum theory after removing this arrow of time, this causal structure.
Yeah, that's very interesting.
Just note that there is still an arrow of time inside the boxes.
I see. There is a notion being put in. So there is a sense of arrow of time which you have built into each of the subsystem, but in general, the global
just locally, yes.
Just locally. With e to the power IHT is not something in the game. I can think it's a null Hamiltonian, for example, where H is a 0. That's one way of. In condensed matter physics, we do it many times. I'm just
okay
because it's a reference. You can.
Yeah. So here, in this approach, in this framework, we just remove any global reference.
Mm-hmm. Okay. Thank you.
Thanks. Okay. So I realized that this was very formal and rather technical, and now I want to come up with to come to a more down-to-earth example of what it could mean in practice to have a quantum indefinite causal structure. And there's a canonical example that has been introduced and studied a lot in the literature, which is this quantum switch. And this is where we can try to get some feeling of what could be some indefinite quantum causal structure. So the quantum switch is a basic example of a circuit with still two operations that we want to perform. These operations, we will have two systems entering the circuit. So a target system in which those operations will be applied. These could be any quantum operations. And a control system. And this control system will precisely control the order in which the target system traverses the circuit. So if the control is 0, that will be the solid line. If the control is 1, that will be the dashed line. So here I sent a 0, so it went through A, then to B. If I send the control qubit in the state 1, it will go to B and then to A. And then the interesting situation is where I superpose 0 plus 1. So if I stand a plus state, then I get a superposition of the two paths. Okay? So I get really a quantum superposition of A being applied first on the target system, then B, plus, that's when the control is in the state 0, plus B being applied first and then A. So in this sense, because the order is in a superposition, then indeed we will get some indefinite causal order, indefinite causal structure. Okay, that's how it can be done in practice with polarizing beam splitters. This was done in a few experiments. The first one being done in Vienna in 2015. That's the experimental setup. This is just to tell you that this kind of circuit can be described as a process matrix. And actually, the process matrix formalism that I introduced on a rather high level and without clear connection to actual relations. Well, this quantum switch is an example of a process matrix. I don't think I have time. If you want, you can ask some more questions about how I describe it. But essentially, the message is that this is an example of a causally non-separable process. Hence, a causal witness can be constructed and can be measured. In some of the few experiments that I mentioned before, precisely a causal witness was measured. The next question is whether with this quantum switch you can violate causal inequalities. Well, unfortunately, that's one of those examples of a causally non-separable process that cannot violate causal inequalities. But still, you can do some interesting things with this quantum switch, and actually, people got excited about it because they realized that this kind of process that allows you to go beyond standard circuits that you use in quantum information processing. So because you can go beyond, maybe you can do some new things. So here's a very canonical example, and actually the first example of application of the quantum switch. And I will just present it to give you some idea and some feeling of how this quantum switch can be useful for certain tasks. So here the example is that I give you two quantum operations, A and B, as given as black boxes. So say these are two unitaries, for instance. And there is the promise that they either commute or anti-commute. And I'm asking you to determine whether they commute or anti-commute. And if you think about it, if you want to determine whether two operations commute and anti-commute with the standard quantum circuit, well, you will need to use them in both orders, right? So you will need to conceive a circuit where you will use A then B, but you also need to use B before A to just compare how the two orders relate. So if you're only given one copy of each black box, then you cannot do it with a standard quantum circuit. But it turns out that with the quantum switch, you can do it, precisely because if you write the output of the quantum switch, then you can write it in a way that you make the commutator or anti-commutator appear. And if you then measure in the plus-minus basis, then you get the answer to the question. So you can see that the quantum switch allows you to do some new interesting things that you cannot do with standard quantum circuits, which have to follow a well-defined causal order. And this has led to a number of investigations of other possible advantages. So there was a generalization to a n-partite quantum switch, where you get some polynomial advantage. There's some advantage in communication complexity, in reducing noise or enhancing classical or quantum communication capacities, and many other advantages inspired by these ones in metrology or quantum thermodynamics. All right, I think I will go in very, very quickly on this part, and then we will wrap up and move to questions. So, as I said, the quantum switch was really the canonical example, and so far this is really the only example that was studied, the only practical example of a causally non-separable process that can be built in the lab that was studied so far. Well, there are some straightforward generalizations with n parties, but then you can think of moving beyond this example. And this is what we did recently in this paper. So the quantum switch is not a standard quantum circuit, which would have to follow a definite causal order, but you can still write it as some kind of circuit. And once you've written it like this, then you can try to generalize what you put inside the circuit. You can have some more general operations like this. I mean, not go into the details, but then you can also come up with more complex circuits following the same kind of ideas. And with this, we could actually now characterize a whole new class of quantum circuits with a quantum control of orders in the same way as for the quantum switch, which in general also give you some processes with indefinite causal orders. And this opens the the way to new applications, new possible applications beyond those of the quantum switch. So I think that's a very exciting direction to investigate what can you do with first the quantum switch and then with more general processes that in principle could be realized in the lab. The bad news is that you can still not violate causal inequalities. But I should say this is the main open questions in the field of how you could possibly violate causal inequalities in practice. Okay, this was an example of a new type of circuit beyond the quantum switch. You can ask me if you want. Just want to highlight that this is non-separable, and it's not just coherent superpositions of different orders, but it's also dynamical order. So where the order between the next two parties here is both coherently controlled, so you can put it in a superposition, but it could also depend on what each party does before. Okay, and I will fully skip this last line. This was also an example of something that we could do now by drawing inspiration of what was done for entanglement and non-locality. And I will just wrap up with this. So, yeah, you can read it. I gave you an overview of the field. Highlighted this fruitful analogy with Bell's non-locality and entanglement, and this can really be inspiring. The type of questions that we're addressing in the field are both very fundamental, talking about indefinite causal structures, causality at the very fundamental level, but this also leads to more applied questions and possible applications, and this is also what makes it quite exciting. And of course, this is a pretty new field, and there are many open questions and some debate about the meaning of all this. There are many new types of processes to investigate, and this question that I mentioned, that whether we can actually really violate causal inequality in practice. Thank you. I will stop here, and I'll take your questions.
Thank you very much, Cyril, for this beautiful talk. And there are a few questions there. Can you read them?
So can I express?
Okay, I can read it for you.
Yeah, I don't see the chat. So.
Yeah. There's a few questions.
So are the questions on the Zoom chat?
Okay, should I read for you?
Yes, please.
Yeah. There's a question from Dipan that does W, I think the process matrix, does W connect quantum functions in A to B in a causal manner? And if so, will the different maps be probabilistic? No.
So this W is so at the very general level, this connects the functions in A and B. So that those functions being the quantum maps that take the input to the output, the quantum input to the quantum output. So in the general framework, this W could be anything that connects these operations in a proper manner by only defining some valid probabilities. And in general, these need not be connected in a causal manner. So I gave you the examples of the quantum state or the quantum channel where these are connected in a causal manner, but more general Ws, they are not necessarily of this form. And this is what makes the whole framework interesting, because you can go beyond these situations with well-defined causal order.
More question from Janki. Does quantum entanglement violate causality? With the general question.
So not in the sense that I was considering here. So if you just share an entangled state and you're looking at whether the correlations that you observe can be embedded in a causal structure in the way that I was considering. So an entangled state will only give you some no signaling correlations. And so for my definition of causality in terms of influence, then this will not violate causality. Okay. So now, of course, quantum entanglement can give rise to non-locality. Non-locality being also called non-local causality. So that's another notion of causality. But for the definition of that I was referring to, that I introduced on my first slide, entanglement by itself doesn't violate causality. Now, there's an interesting situation where you can have a process matrix that is causally separable, but if you attach some entangled state to it, then it becomes causally non-separable. And this was called activation of non-causality. So in some cases, it could help somehow an entangled state could help process matrix exhibit non-causality and violate causality.
Thank you. Let's say maybe I have a question. That is, you shifted from device independent to device dependent. What exactly the difference? I mean, device dependent scenario. What additional assumption you introduced?
Okay, so this is something that is this distinction is very standard in quantum foundations, quantum animation, where when we investigate entanglement and non-locality. Mm-hmm. So the distinction is whether you know what your devices are doing. Mm-hmm. So whether you know, for instance, that they can be described by a given theory, by quantum theory, or if you allow for any theory, or in the case of device dependent or device independent, whether you know exactly what the devices are doing. So if I give you a device and I say, okay, this is measuring along this direction, along the Z direction, then if you make any conclusion that assumes that indeed the device is actually measuring along the Z direction, then all those conclusions will be device dependent. Okay.
My question was a little different. I'm thinking that if it is device independent, test is already done, or all the tests are already, we have device dependent and experimental test.
Okay, for those questions about
using the quantum switch and...
Okay, so for the quantum switch, so as I said, the quantum switch cannot violate any causal inequality.
Yeah.
Okay. And this is a bit disappointing because then this means we cannot really observe non-causal correlations. And that also means that we need to essentially measure a causal witness.
So,
and now, when you measure a causal witness, then you need actually to trust what your devices are doing. Yeah. So this will be device dependent.
Yeah.
That's in the part of about device dependent. So anything that could be done so far was device dependent on the quantum switch.
Also, you said
ideally, of course, we would like to go device independent.
Independent scenario, yeah. So one point maybe I say I don't understand, because it is kind of coming from the Bell violation, such kind of. You got the causal structure, it gives the 3 by 4, 0.75 probability. But in quantum value, it was 0.82. It was not up to 0.85, right?
No, that's not the standard.
Not the standard
Johnson bound or something like that. No, that's a very weird number, but
yeah. I mean, 0.85 it matches with our intuition. I mean, that's in quantum mechanics, we can expect that, but 0.82 is a very strange number. And actually the process matrix that gives you this value or the actual measurements that you need to do to reach these values, they have no simple form. So that does mean that the scenario is that what I understood, that quantum switch is not device independently tested yet, right?
No.
Because you don't have the causal inequality.
Right.
Yeah.
So,
yeah. So without process matrix, this can also be the whole exercise you can, or many people are doing. That can be done without using the process matrix, because process matrix is little complicated. I know. I once tried. It's complicated, right?
So sorry, I was trying to reach the chat. I didn't quite get the question.
Yeah, I am telling that the whole the work in this indefinite causal order, that can be done without using the process matrix as well, right?
Okay, so there are some different approaches to indefinite causal orders.
Mm-hmm.
So there's some other frameworks that were proposed. Most of them are closely related to process matrices.
Mm-hmm.
And you can, of course, study the quantum switch without introducing the framework of process matrices. And actually, the quantum switch itself was proposed in a preprint in 2009, so 3 years before the process matrix was introduced. So at the beginning, they were not describing it as a process matrix.
Mm-hmm.
But that also means that they couldn't say that this is causally non-separable, because this notion wasn't defined yet.
Mm-hmm.
And also the process matrix formalism allowed us to introduce this tool of causal witnesses and to verify now in practice this causal non-separability of the quantum switch.
Okay. There's one more question, that could quantum switch, it's from Deepan again, could quantum switch with higher dimensional control variables violate causal inequality?
No, so the short answer is no. So indeed, you can generalize the quantum switch. So instead of having two operations that you put in a superposition of orders, you can have some more operations, and then you can have n operations in n factorial different orders, and you have a higher dimensional control that controls all this. But even this doesn't allow you to violate the causal inequality. And in fact, all this is an example of what we generalize in this work, this recent work with Vex et al. At the bottom. We generalized even this quantum switch to more general quantum circuits with quantum control this way, and the whole class that we could come up with. For the whole class, we could prove that they cannot violate causal inequalities. So essentially, any process matrix that can violate the causal inequality, I have no idea of what it means physically. I cannot write it as a circuit where I can superpose some orders. I just have no idea. And that's one of the exciting open problems in the field, to try to make sense of this formalism.
Alok, can I ask a question?
Sure.
Yeah, so I think it's very interesting. What you're saying is within quantum mechanics, consistent quantum mechanics, there is a provision for violating this inequality. You can mathematically write it down. What you do not know is his physical realization, and something which is very recent development which comes to my mind. Maybe I want to point my finger that direction. You might have noticed this topological state of matter where one is thinking of qubits which are totally non-local. And the information are encoded by braiding operations. And, these are essentially the knot theory, which defines the state of matter in this case, the topological state of matter. So maybe these are objects, and these have long-range entanglement and so on. And probably, I think I would imagine that local qubit won't do such things, because we are trying to implement things via local qubits. But this topological state of matter essentially allow you to have qubits which are absolutely non-local in nature. For example, using Majorana fermions, they're very non-local qubits. And if you have such non-local qubits, maybe there is a possibility that you get a physical realization of, because I think the approach which you're right now using of physical realization is local operations. So this is just, this is something which, as you're saying, this is something which comes to my mind.
Okay, well, thank you very much for the comments. Yes, that's a very, very good comment. I should look into that. there could be some ideas to look into there. So the claim once again is that for the circuits that we defined, there could be no violation of causal inequalities. We are not claiming it's everything that can be done with quantum theory. This other paper that I cite here, they have a very similar claim, and they claim a bit more that this is really with anything that can be done with quantum theory cannot violate causal inequalities.
Okay. Is that the case? I mean, that's the question then. Is it well proved, well accepted?
That's the case. That's the claim of that other paper, which is a bit stronger than our claim. But
that's the strongest claim you can have.
Yeah, I feel
that's the strongest claim.
There are still some assumptions in their paper. So
I see. So there is a room. You are saying there is a small, even if small, but there is a room for.
I still believe that there is a room for finding something interesting. So the direction that you're suggesting seems a good one to explore. So the only thing is that we don't, as I answered another question before, we don't just need entanglement and very highly entangled states. It's also about the process, about how we connect operations that we will perform on the
Right. And maybe the non-locality in those systems, which is intrinsic to them, maybe helps in certain way.
It could be helpful, but that will not be enough, essentially.
Yeah. Okay.
But thanks anyway for the very good comment.
Thanks.
One more question. One student is asking: please explain a little bit about the gravitational quantum switch.
Okay, so the example that I showed about the quantum switch, I showed a possible realization as a tabletop experiments, and indeed the experiments that were performed were really tabletop experiments, where you use essentially typically polarization. You put polarization in a superposition state, and that's your control. There has been some debate about whether this really implements a quantum switch or whether this is just a simulation of a quantum switch. And so there's been some proposals for possibly more convincing realizations of the quantum switch. And one proposal was this gravitational quantum switch. And the proposal is very far-sketched. It's really that you want to essentially superpose causal structures. If you want to have indefinite causal structure, you may want to superpose causal structures. And the way you could do that would be to have a superposition of two big masses that will create different gravitational fields. And by having these in a superposition, you actually create a superposition of two gravitational fields and two metrics, and then you can have some indefinite causal orders in those indefinite structures, in this superposition of structures. So that's a proposal to answer some of the questions that are posed in this debate of whether we are considering re-implementations of the switch or simulations. And I think that the problem that these people who say that these are only simulations, the problem they have is with the definition of events. So I started my talk by defining what I mean exactly by an event, but people coming from GR would define the events differently, typically as a point in space-time. And of course, if you try to identify points in space-time in the tabletop experiments, then clearly you don't realize a quantum switch, and you don't put points in space-time in a superposition.
So there are not many relevant questions today. So this is all. And so Cyril, thank you very much once again for this beautiful talk, and it was very nice to see you once again.
Yeah, nice to see you, and thanks for the
invitation. And Sorin, you want to say something?
No, yeah. Thanks for the wonderful talk. Yeah. Enjoyed it very much.
Yeah, I think Professor Panikkar is not there. Professor Panikkar, are you there?
Shant is not here. He's here.
Yeah, Okay, Cyril.
Okay, thanks a lot for the
Thank you very much.
Hope to
Let's
see you
where we can
in
meet
real life.
Yeah, you can meet again. Yeah, okay, bye.
Definitely. Thanks, and enjoy the summer school.
Thank you, sir.
All the best. Stay healthy.
Yeah, thank you.
Oh, yeah.
Just.
Yeah, Professor Panikkar, convener and organizer.
I hope some of the students will pick up this circuit and try to implement it.
Thank you, sir. Okay.
It's an excellent area, actually.
Yeah.
To start with.
Yeah, it's a very exciting field. So I also hope many people get into it. And we need some fresh ideas from new people in the field.
Yeah.
Yes,
I think
I'm just curious. Has somebody implemented these kind of circuits in IBM or any other platform?
No, I don't think so. No, not that I'm aware of. No.
Yeah, that may be one thing some of the students may try.
Yeah. They can understand a bit how the research works.
Yeah. It could certainly be a good exercise to look at that. Yeah, at least to simulate this kind of circuits. Absolutely, yeah.
Thank you very much. Thank you for your time.
Yeah.
Thank you for the invitation once again. Hope you have a very enjoyable summer school.
Thank you. Okay, bye. See you.